Picture a liquid that goes through at least 10 different transformations before it ends up in the tank of a truck, tractor, or generator. It's boiled, compressed, broken down into molecules, reassembled, cleaned with hydrogen, and tested dozens of times. All of this so an engine can run for hours under load, in scorching heat and freezing cold, without failures or surprises. Diesel fuel seems ordinary, but it's actually one of the most complex products of modern industry, where behind every gallon stands engineering, temperature, and cold calculation. Diesel fuel doesn't just appear from crude oil, like gasoline from a pump. It's the product of a long, hot, and highly controlled chain of processes, where crude oil is gradually transformed from a dark, heavy liquid into a precisely defined mixture of molecules capable of running reliably in an engine. Everything starts with oil, but then it's literally broken down into components, sorted, cleaned, and reassembled, this time in the right form. Crude oil begins its journey far from the refinery, at oil fields, where it's lifted from the Earth's depths through wells. Along with the oil, water, gas, sand, and small rock particles come to the surface. So right at the extraction site, it's partially settled and the largest impurities are separated out. Once it's out of the ground, the oil hits the road. Most of the time, that means pipelines, continuously pumping millions of tons of liquid across hundreds, even thousands of miles. Where there are no pipes, tankers or rail cars take over. Either way, by the time the oil reaches the refinery, it's still far from ready. Before processing can begin, the crude has to be prepped. It almost always contains water, dissolved salts, and solid particles. Leave those in, and they'll wreck the equipment fast. Salts cause corrosion, water messes with stable heating, and solids wear down pumps and pipes. So the oil gets heated and run through desalting and dehydration units. There, it's mixed with fresh water to wash out the salts, then an electric field forces the water to separate and settle. After that, the crude is much cleaner, and a lot safer for what comes next. The prepared crude oil enters the refinery's main unit, the atmospheric distillation column. This is a tall metal tower, like a multi-story building, with dozens of horizontal trays or packing material inside. The column maintains a constant temperature difference. It's super hot at the bottom, and the higher you go, the cooler it gets. The oil is first heated intensely in furnaces, usually to around 660 degrees Fahrenheit, and then injected into the middle of the column in this hot state. Once inside, the oil starts behaving completely differently than it did in the pipeline. It partially vaporizes, creating a mixture of vapor and liquid. Lighter components with lower boiling points quickly turn to vapor and rise upward. Heavier fractions stay lower or flow all the way down to the bottom. Each level of the column corresponds to its own temperature range, so the vapors condense exactly where they're comfortable. As a result of this process, crude oil is essentially taken apart
where it
into its
remains
components.
hottest, settle lubricating oils and heavy residues.
Medium ones below, and the heavy residues remain at the very bottom. Everything happens without chemical reactions. The molecules don't break down or change. They simply separate based on physical properties. It's from this point that the real life of crude oil begins as raw material for fuel, lubricants, and dozens of other products, because each fraction obtained will follow its own technological pathway. This is where diesel fraction first appears. It's heavier than gasoline and kerosene, so it condenses lower down, but it's still light enough to be a liquid fuel. This isn't finished diesel fuel yet, just a halfway point, gasoil. It packs a lot of useful energy, but also plenty of sulfur, nitrogen compounds, and unstable molecules that engines hate. The gasoil that comes out of crude distillation is still miles away from the diesel fuel you pump into your tank. It looks similar, sure, but its makeup is dirty by modern standards. It contains sulfur, nitrogen compounds, traces of metals, and unstable hydrocarbon chains that oxidize easily and form carbon deposits. If you fed this stuff straight into an engine, it would quickly destroy the injectors, catalytic converters, and exhaust cleaning systems. That's exactly why gasoil has to go through a hydrotreating stage. At this stage, the fuel gets channeled into special reactors where they create extremely harsh conditions. Temperature there typically hits several hundred degrees, and pressure runs dozens of times higher than atmospheric. Hydrogen gets fed into the gas oil, and this mixture passes through a catalyst bed. The catalyst doesn't get consumed in the process, but it's what forces the chemical reactions to go fast and in the right direction. Without it, purification would either be way too slow or just flat out impossible on an industrial scale. When the gas oil contacts the hydrogen, a series of reactions kicks off. Sulfur-containing compounds break down, and the sulfur converts into hydrogen sulfide, a gas that's easy to separate from the fuel. Nitrogen compounds transform into ammonia, which also gets removed from the stream. At the same time, hydrogen heals unstable molecules. Double bonds get saturated, and fragile structures rearrange into more stable ones. As a result, the fuel becomes chemically calmer, oxidizes less during storage, and behaves better during combustion. After the reactor, the gas oil is cooled and sent to separation units. There, gaseous products, hydrogen sulfide, ammonia, excess hydrogen, are separated from the liquid fuel. Hydrogen is usually recycled back into the process, while harmful gases are sent for further processing or neutralization. It's thanks to this stage that sulfur content in diesel fuel drops by tens or even hundreds of times, down to levels that meet modern environmental standards. The importance of hydrotreatment can't be overstated. It doesn't just cut harmful emissions, it directly impacts engine life. Cleaner fuel puts less wear on fuel injection systems, doesn't poison catalytic converters and particulate filters, burns more consistently, and keeps the engine running predictably. This is really the stage where gas oil stops being a semi-raw material and starts becoming actual diesel fuel suitable for 21st century machinery. But the process doesn't end there. Some diesel components don't even come from primary distillation. Heavy petroleum residues go through vacuum distillation, where reduced pressure extracts even more useful fractions. And if that's still not enough, cracking enters the picture. A process where large, lazy molecules are literally broken down into smaller ones. Hydrocracking is especially critical for diesel because it produces fuel with better combustion characteristics, a higher cetane number, and fewer impurities. After all these stages, different diesel components get blended together. This isn't some random pouring from one barrel to another. It's precise recipe-based mixing. Engineers dial in the proportions so the fuel meets standards. Good ignition, no thickening in the cold, minimal smoke, and no damage to the fuel system. At this stage, they add additives, tiny amounts, but with big impact. They improve lubrication properties, protect against corrosion, reduce foaming, and help the engine start up in winter. Seasonality is a whole different story. Summer diesel is thicker and more stable in warm temperatures. Winter diesel undergoes additional processing. Components that could crystallize in the cold are removed or modified. Otherwise, at 14 degrees Fahrenheit, the fuel starts turning into a cloudy sludge that clogs the filters. For extremely cold regions, they make Arctic diesel, lighter, pricier, and way more complex to produce. Once the fuel's ready, it's stored in tanks, then shipped to fuel depots, and finally to gas stations. But even along that route, it can still be tested, filtered, and adjusted. Diesel isn't a product where you can afford close enough. One small mistake at the refinery can turn into widespread equipment failures. We're standing at a modern asphalt plant. It smells like hot tar, heated stone, and a little bit of my morning coffee, which I nearly spilled when I saw the scale of this metal structure. Most people think asphalt is just some black goop they smear on the road, but it's actually a whole science where every pound and every degree matters. We're about to break down this process into parts and see how a pile of rocks and a barrel of sticky liquid turns into a perfectly smooth highway. It all starts at the aggregate storage yard. These are massive mountains of crushed stone and sand you see behind me. This is serious business. The rocks are sorted by size. We've got really fine screenings, And we've got fractions half an inch or even 3/4 of an inch. Why does this matter, you ask? Because asphalt is like a cake. If you put in too many big nuts and not enough flour, it'll just fall apart under your car's wheels. A special loader grabs this crushed stone and dumps it into huge steel bins. Each container holds about 10 or 15 tons of material. Then begins a long journey on a conveyor belt. This rubber track stretches for dozens of feet and carries the stone to the heart of the plant, the dryer drum. Look at this giant metal tube slowly rotating. It's about 30 or 40 feet long. Inside it, a real flame roars. Why do we roast stone? Because there can't be a single drop of moisture in it. If water gets into the hot mix, it'll turn to steam and punch holes in your future asphalt, what we call voids. The temperature inside this drum climbs to 300 or even 350 degrees Fahrenheit. That's way hotter than your oven when you're baking pizza. Once the stone is properly roasted, it becomes super hot and bone dry. Now it needs to be lifted to the very top of the plant. They use an elevator for this, a vertical chain with buckets that stretches up 60 or 70 feet. Up there at the top, the scorching aggregate gets screened again through a set of sieves. It's like a final quality check to make sure no random wrong-sized rock messes up our road. Now we get to the star ingredient, bitumen. That's the same black sticky stuff that holds all the stone together. It's stored in massive vertical tanks that are constantly heated. If the bitumen cools down, it becomes hard as a rock, and we can't do anything with it. Each of these drums can hold up to 20 or 30,000 gallons of this black liquid. The bitumen is fed into the mixer under high pressure. It looks pretty epic, although peeking inside while it's running is a bad idea, unless you want to become part of the road. The actual mixing process happens in a giant mixer. They dump in a precisely measured amount of hot stone, add mineral powder, think of it like cement dust for thickness, and pour in the liquid bitumen. One mixing cycle takes about 40 or 50 seconds. In that short time, the mixer blades have to coat every single grain of sand with a thin layer of black gold. Imagine the responsibility. If you mix it poorly, the asphalt will start crumbling after the first winter. The finished asphalt comes out of the mixer at around 320 degrees Fahrenheit. It's basically molten black lava. From there, it either gets dumped straight into a dump truck bed, or it heads to a storage silo. These silos look like space rockets sitting on a launch pad. They can hold 200 to 300 tons of hot mix for several hours while maintaining temperature. This lets the plant run non-stop, even when trucks get stuck in traffic jams. I'm standing right now at the control panel. People sit here watching every pound of weight and every degree of heat on their monitors. A modern plant is a fully automated system. The operator just enters the recipe, and the computer decides how much sand, how much aggregate, and how much bitumen to mix. This eliminates human error, because a mistake of 0.1% in the formula can cost millions if the road has to be redone a year later. You've probably heard that asphalt is one of the most recyclable materials in the world, and it's true. This plant has a special unit for adding old asphalt that's been milled off other roads. They grind it up and put it back to work. It's awesome because we're not just tossing old rocks into a landfill, we're giving them a second life. The recycled material can make up 20 or even 30% of the new mix. That's good news for the environment and for the builder's wallet. Let's just take a quick detour right now and peek at how this goes down. Dawn breaks. The highway's blocked off with orange cones, and there's this thick steam rising from the hot asphalt. Feels like we're on the set of a volcano eruption movie. Our dump truck slowly backs up to the paver. This massive iron-tracked machine worth close to $500,000. The truck bed lifts, and 20 tons of black, steaming mass at 300 degrees Fahrenheit pours straight into the receiving hopper. Inside the paver, powerful augers are at work. Giant screws, just like the one in your meat grinder at home, only 12 feet long. They spread the hot mix evenly across the entire width of the lane. Behind the machine comes the screed plate, which doesn't just level the asphalt. It vibrates with crazy force to compact it initially. The machine leaves behind a perfectly smooth, black-as-night carpet, but it's still too soft. Step on it now, and your shoe stays there forever. And that's when the heavyweights enter the scene. The rollers. First comes the vibratory roller, weighing about 10 or 12 tons. Its steel drums rotate while simultaneously pounding the road at a rate of 40 or 50 strikes per second. You feel this vibration even through the soles of your sneakers from 30 feet away. This is necessary to squeeze out all the air and make the pavement solid. Behind it rolls a pneumatic tire roller on rubber wheels. It smooths the surface, sealing the tiniest pores so water can't get in. One pass after another, and we get a road that'll last 15 or 20 years. Let's go back to the plant. Another interesting point is air cleaning. You see that big box next to the drying drum? That's a baghouse filter. Inside it are hundreds of long fabric bags that capture dust. Only clean water vapor goes into the air, and all the dust is collected and goes back into the asphalt. So stories about these plants being super dirty, that's ancient history. Modern production is cleaner than the kitchen in most fast food restaurants. Now about volumes. A mid-sized plant like this can put out around 240 tons of asphalt per hour. Just to put this in perspective, that's roughly 12 big rigs worth of material. In a single 10-hour shift, this metal giant produces enough asphalt to lay several miles of new 2-lane highway. That's insane speed and massive responsibility. When a dump truck pulls up under the hopper, about 20 tons of smoking black mass pours onto it. Then the driver covers the bed with a special top so the asphalt doesn't cool down on its way to the paving site. If the temperature drops below 250 degrees Fahrenheit before it gets rolled out, you won't get a quality road. So logistics here is a real race against time. Watching one of these plants operate is like watching a really big, really complicated food processor. Nothing here is wasted. Every motor and every sensor performs its exact function. And while from the outside it looks like a pile of smoking, rumbling metal, it's actually a triumph of precision and engineering calculation. Every mile of highway we drive on vacation or to work started right here, in this hot, noisy place. Stick with me. We've got plenty more fascinating machinery and weird mechanisms coming up that make our lives more comfortable, even if we usually don't notice them. In every country, asphalt is just a road. But in Dubai, it's a challenge to nature. Here, air temperatures reach 122 degrees in the shade, while the road surface heats up to 160. Regular asphalt would melt within just a few days, but engineers found a way to make it survive. Polymers that hold their shape even at 176 degrees, geotextile membranes that breathe, and sensors that detect defects before human eyes can spot them. Why don't these roads melt like ice in the sun? And what strange technology did they test to make them actually dry after rain? Watch till the end. The finale will surprise you. Standard asphalt consists of stone aggregate and bitumen, a dark, thick substance that holds the mixture together, making it uniform and strong. However, bitumen has one weakness. It starts to soften at temperatures around 113 degrees Fahrenheit. For countries with moderate climates, this isn't a problem since road surfaces rarely reach such heating levels. But Dubai has completely different conditions. There, summer air can heat up to 122 degrees in the shade, while the road surface under direct sunlight can reach 160 degrees. Under such conditions, regular asphalt would literally behave like warm rubber. It would become soft, start deforming under vehicle weight, and in places simply slide off slopes. Plus, sharp temperature changes between scorching days and relatively cool nights would cause cracks to appear. In countries where occasional short heat waves occur, people might not immediately notice these processes. Sure, we sometimes get 104 degrees in summer, but such temperatures don't last long, and the surface deteriorates slowly, gradually. In Dubai, however, high temperature isn't just present, it's constant and stable for several months. This means asphalt is under continuous stress, and if you don't account for this factor, the road literally won't survive. That's exactly why engineers had to find a solution that would allow asphalt to maintain its shape even under extreme heating conditions. They replaced regular bitumen with modified bitumen, with polymer additives that change its physical properties. Such bitumen holds its shape at temperatures up to 176 degrees Fahrenheit. This means even when the road surface heats up to maximum levels, the material still remains stable, doesn't flow, and doesn't change structure. The difference might seem small at first glance. What's a few dozen extra degrees? But this exact difference makes Dubai's roads smooth, even, and durable, even when it's almost impossible to breathe from the heat around you. So what is this modified bitumen? The process is based on mixing bitumen with polymer additives. Polymers act like a reinforcing network at the molecular level. They stretch the bitumen structure, making it more elastic and heat-resistant. As a result, the asphalt doesn't soften. It maintains stability and shape even when heavy bus or truck wheels press on it for hours. The mixing process also isn't limited to just adding polymers. It's crucial to properly select the stone aggregate composition. Stones of different sizes create a framework-like structure, and bitumen here acts not as the main material, but rather as what connects the elements together. If the aggregate is selected incorrectly, bitumen will have to take on too much load, and even the modified mixture will lose stability. Therefore, asphalt composition is always a precise calculation of material ratios that don't just connect, but work as a unified system. But asphalt is just the surface. Hidden beneath it is a multi-layered sandwich that determines the road's durability. The first layer is sand, but regular sand won't work. It's mobile, can shift, and the road would lose its evenness within months. So sand is stabilized by mixing it with cement or special substances that make the mixture less mobile. Next comes a crushed stone layer that provides hardness and distributes load. Special geotextile fabrics can be laid between layers, preventing settling and material mixing. Geotextile works as a membrane that allows water to pass through, but doesn't let soil particles mix. This keeps the construction stable for many years. The way asphalt is actually laid also plays an important role. Work is usually done at night when temperatures are lower. This is necessary so bitumen cools evenly and gains the required hardness. If you lay asphalt during daytime heat, its surface will cool unevenly, creating stress in the structure that will eventually lead to microcracks. After laying, roads are regularly checked using special machines equipped with sensors and thermal imaging cameras. If sections are found where temperature is too high or irregularities appear, they're repaired immediately, not waiting until the problem becomes visible to drivers. Experiments with cooling coatings deserve special mention. In some districts, asphalt is painted or covered with a special compound that reflects sunlight and reduces surface heating by 10 to 15 degrees. This is important in pedestrian areas since road surface temperature affects how hot the air gets at foot level. This way, even a regular walk becomes less exhausting. In Dubai, roads aren't left unattended until large potholes appear. Control happens constantly and systematically. Special vehicles with measuring equipment travel highways and city streets, recording the smallest irregularities. Sensors read surface deviations, and computers compare them to standards. If there's suspicion of overheating or beginning deformation, the section is checked with thermal imaging cameras. High temperature indicates that bitumen is losing rigidity, and the surface might start settling. Thanks to such monitoring, repairs are done not when it's too late, but when the first changes begin. Repair work is conducted mainly at night when temperatures are lower and material cools evenly. This extends the road's service life and avoids repeated damage. The approach is based on the idea that infrastructure should work continuously, not wait for the moment when it becomes a problem for drivers. According to Dubai municipality data, after switching to polymer-modified mixtures, the number of deformation waves on roads decreased by approximately 40% during the first 2 years. Meanwhile, road surface service life increased on average from 7 to 10 years to 12 to 15 years before the first major repair. This significantly reduces overall infrastructure costs. Although initial polymer asphalt installation costs are higher by approximately 15 to 20%, long-term savings can reach 50% due to reduced repair needs. There's also data on experimental light reflective coatings being tested in residential areas and near pedestrian zones. On average, such coatings reduce road surface temperature by 10, or even all 14 degrees, depending on conditions. According to observations, in areas with cooling roads, air temperature at pedestrian foot level also drops by 2 to 3 degrees, reducing thermal load on people and making outdoor stays more comfortable. Statistics also show that, with early detection of surface microdefects, their elimination takes on average 3 to 6 hours, while if you wait for visible damage to appear, repairs can last from several days to several weeks and require closing road sections. Therefore, the city focuses on regular monitoring. In 1 month, control vehicles can cover over 80% of the city's road network. Dubai once tested asphalt that absorbs solar energy, then radiates stored heat at night to dry roads faster after rare rainfall. Turns out, the surface works like a giant thermos. During the day, it accumulates energy, and at night gradually releases it. The experiment showed such roads can dry 30% faster. And this is really needed, because after desert rain, water doesn't absorb into the ground, but can stand on asphalt for hours or even days. So the technology solves a problem that doesn't even exist in most countries. You know how this experiment ended? Imagine construction that's not just strong, but super lightweight, durable, and eco-friendly all at once. That's exactly the revolution that fiberglass rebar represents. A modern material that's gradually replacing traditional steel reinforcement in countries around the world. China is especially aggressive in producing it, a giant controlling a massive chunk of the global market. But what is this secret material that's changing the game? And why does geopolitics play just as big a role here as technology? Let's dig in. Fiberglass rebar consists of reinforcing rods made from a composite material based on fiberglass soaked in special resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and holds up under harsh conditions. Think acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs close to 1 pound per foot of length, while fiberglass rebar weighs about 1/4 pound for the same size. This means it's easier to work with, requires less spending on transportation and installation, which makes construction faster and cheaper. China plays a leading role in global fiberglass rebar production. Factories, located mainly in the eastern and central regions of the country, are equipped with modern pressing, forming, and fiberglass polymerization lines. Chinese companies produce over 500 million pounds of these materials annually, with exports accounting for roughly 60% of total global volume. China's huge advantage lies not only in scale of production, but in price. Thanks to low electricity and resource costs, Chinese products are often cheaper than competitors from the USA and Europe. But this is already triggering intense geopolitical discussions. If you look at the bigger picture, fiberglass rebar has become a real hot potato in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. This secret aspect is this: China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in countries across Asia, Africa, and Latin America, Beijing actively promotes this material through its global construction corporations working within the Belt and Road Initiative. This allows China to not only increase its presence in the global construction market, but also strengthen economic influence in regions through control over construction resources. The trend of using fiberglass rebar isn't just about savings or new materials. It's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the USA, where the number of bridges, roads, and buildings constructed using lightweight composites is growing. Unlike metal, this material doesn't corrode, so infrastructure becomes more reliable and durable. According to reports from the American Association of Building Materials, on average, the cost of construction using fiberglass rebar drops by 20%, and the service life of structures doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, reduced environmental impact, and industry growth. If you're building a bridge or a high-rise, instead of heavy steel rebar, you use thin fiberglass rods. They can be longer, lighter, and simpler to install. Plus, you don't have to worry that after years, they'll start rusting and causing concrete deterioration. China is already actively using its fiberglass rebar on huge construction sites. In the capital districts of Beijing, Shanghai, and Guangzhou, they're installing new highways and bridge crossings using these materials. Around the world, Chinese companies supply this rebar for projects in the USA, Europe, and Middle Eastern countries, strengthening their technological and economic presence. Everything starts with glass, the raw material for making fiberglass. Glass is made from a mixture of sand, limestone, and soda. These ingredients are sent to large furnace ovens, heated to temperatures of 2,700 degrees Fahrenheit. Here, the mixture melts, forming liquid glass. Then the molten glass passes through special openings called spinnerets, forming thousands of thin threads. These fibers are cooled and collected into bundles. This creates primary fiberglass, thin, flexible, and strong threads. To give the fibers necessary properties, they're treated with a special chemical solution, an organic binder or silane. This coating ensures strong adhesion between the fiberglass and the polymer matrix that will follow. The treated threads are collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main stage, forming the composite matrix. The raw material for this is polymer resins, usually epoxy, polyester, or vinyl, which have high strength characteristics and provide resistance to moisture and chemical effects. The fiberglass bundles are dipped or soaked in the polymer resin solution. The fibers are evenly coated with polymer, and excess is removed so there are no lumps and irregularities. The prepared wet bundles are fed into a special forming line, an extruder. Here the molten composition is pushed through forming openings, giving it the shape of a rod or bar of the required diameter. Then comes an important operation, drawing and polymerization. The finished reinforcing rods are immediately sent for cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a single structure. Size and shape control is very important, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard fiberglass rebar diameter can range from 1/4 inch to 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During production, an action occurs through forming rollers that creates ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It holds firmly in the concrete mass and doesn't slip under loads. At the end of the production line, workers or automation cut the reinforcing rods to standard lengths, usually 20 feet or 40 feet. The rods are packed in bundles that are convenient to transport and store. Each batch of products undergoes testing for strength, flexibility, and corrosion resistance. Manufacturers often provide warranties for rebar service life of over 50 years, which is several times longer than the service life of ordinary metal reinforcement. Fiberglass rebar is gaining increasing importance in modern construction thanks to its lightness, strength, and corrosion resistance. Next, you'll see some of the most interesting projects where this innovative material is actively used. Delhi Metro Phase in India, a large-scale metro project where this rebar is actively used to reinforce tunnels and structures. This helps extend the service life of structures and reduce the weight of building materials. Jizan Flood Mitigation Channel, Saudi Arabia, the world's largest project using fiberglass rebar, involving reinforcement of long channels for flood control. Over 11 million meters of fiberglass rebar were used here, designed to ensure high resistance to harsh environments. Muskrat Falls Hydroelectric Project, Canada. Rebar manufacturers supply material for reinforcement that guarantees a long service life for the hydroelectric station, especially in conditions of contact with water and high humidity. Sunshine Skyway Rest Area. Seawall, USA, Florida. Marine structures where fiberglass rebar is the ideal material due to corrosion resistance in salt water. Here it reduces the need for repairs and extends the service life of the walls. Alligator River Bridge, USA, North Carolina. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Canadian Tunnels. Toronto TTC North Subway Extension. A project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic movements. Today, we're not at some sleek, modern factory. We're heading back in time, to an era when the entire world was engulfed in flames, and one nation that had peacefully built cars and refrigerators did something absolutely mind-blowing. This is the story of the arsenal of democracy, how American industry churned out so much weaponry in just a few years, it could have armed several planets. And we're looking at its crown jewel, the legendary flying fortress, the B-17 bomber. I spent weeks digging through archival blueprints, photographs, and records to tell you how a country that was making sedans for housewives yesterday started rolling out one bomber every single hour. So it's December 1941. Pearl Harbor's in flames, and America enters World War II. And the first question facing the government, where do we get planes? The B-17 bomber, developed by Boeing. It's an engineering marvel, but they're building barely any, almost one at a time. And the country doesn't need dozens, it needs tens of thousands of these machines. So President Roosevelt throws down the gauntlet to American industry, and that industry answers. And how it answers. Enter automotive giants like Ford and aircraft companies Douglas and Lockheed. They're told, guys, forget about cars. From now on, you build bombers. And that's when the real madness begins. Picture this. Ford, a company that had never built planes before, constructs from scratch in the middle of a Michigan cornfield, the world's largest factory at the time. Willow Run. This isn't just a factory, it's an entire city under one roof, a mile long. Over 40,000 people work here, many of them women coming into manufacturing for the first time. And they face a task that seems impossible. Put the production of a giant, complex bomber on an automotive assembly line. Nobody had ever done this before. You get why it was women, right? When America entered the war, millions of men, factory workers, farmers, mechanics, put on military uniforms and shipped out to the front. And suddenly, the factories that needed to produce tanks, ships, and planes sat empty. The country faced a massive labor shortage. So the government and industry turned to people they'd barely considered for heavy manufacturing before. Women. A powerful propaganda campaign rolled out. Famous posters showing a strong woman in a work bandana, flexing her bicep with the words, "We can do it," appeared across the country. And women answered the call. Millions of housewives, waitresses, secretaries, and recent high school graduates went to work in the factories. For them, this wasn't just a paycheck. It was patriotic duty, a way to do their part for victory, while their husbands, brothers, and sons fought thousands of miles from home. They proved they could do men's work just as well, sometimes better, becoming the unstoppable force that allowed American industry to work miracles. And here's where the American government and industry made some incredibly powerful moves. First, the government essentially forced Alcoa to share its technology and funded the construction of dozens of new, massive aluminum plants across the country. Entire cities were built, for example, in the industrial states of Washington and Tennessee. Why there? Because aluminum production is an insanely energy-intensive process. It relies on electrolysis from alumina, and that requires cheap electricity. And in these exact regions, the government had just finished building giant hydroelectric dams on the Columbia and Tennessee rivers. It was a perfect match. Huge amounts of clean, cheap energy waiting for someone to use it. Second, raw materials. The main raw material for aluminum is bauxite. Most of it had been imported from South America before the war. When the war started, German submarines began hunting merchant ships, and that route became dangerous. So America dramatically ramped up mining of its own bauxite, mainly in Arkansas, and secured the sea routes from the Caribbean as much as possible. But the most amazing part of this story is the grassroots movement. The government launched a massive patriotic campaign with the rallying cry, "Turn in aluminum for victory." School children, housewives, Boy Scouts, the entire nation started collecting aluminum scrap. People turned in old pots, pans, milk cans, parts from household appliances. It didn't have decisive economic significance, but it had a colossal psychological effect. Every American felt that their old pot could become part of a flying fortress wing that would fly off to strike the enemy. As a result of these titanic efforts, in just a few years, from 1940 to 1943, aluminum production in the US increased sixfold. The country didn't just cover its own needs, it started supplying this strategic metal to its allies. And that's how, through the combination of government will, industrial might, and the patriotism of ordinary people, America transformed a scarce pot metal into an endless stream of winged metal that became the lifeblood of its bomber armada. After stamping, each part needed 2 holes drilled on each side for rivets. And that's when the women stepped onto the stage. The legendary Rosie the Riveters. Thousands of young women who just yesterday were housewives or waitresses now stood at workstations, drilling these holes with incredible speed and precision. And then the real concert began. Thousands of pneumatic riveting hammers pounding aluminum simultaneously, creating a deafening non-stop roar. This was the sound of the arsenal of democracy being forged. Women worked in pairs. One held a massive bucking bar from the inside, while the other hammered the rivet from outside. Each rivet had to be perfect, because the aircraft's strength depended on it. And this is where Ford unveiled its main automotive trick, modular assembly. They didn't try to build the entire airplane in one place. Instead, they broke it down into large sections, or modules. In one shop, thousands of people assembled just the nose section of the fuselage. In another, just the center section with the bomb bay. In a third, gigantic wings, each over 50 feet long. Each section was assembled on its own mini assembly line, where it was packed with everything necessary. Miles of wiring were run, hydraulic lines installed, equipment mounts fitted. This allowed dozens of teams to work in parallel, without getting in each other's way. And then, these ready-made sections, packed with internal modules, looking like giant chunks of an aluminum construction set, got wheeled over to the main assembly line. This was the climax, a line a mile long. At the start, there's just the center wing section. Then 2 fuselage halves get joined to it. The whole structure moves freely forward. At the next station, they attach the nose and tail sections. Further down, they mount the massive wings. And so, step by step, right before your eyes, from separate pieces, a gigantic, nearly 100-foot aircraft takes shape. At the final stations, they install 4 powerful Wright Cyclone engines, each churning out 1,200 horsepower, mount the landing gear, glaze the cockpit, and of course, fit its main argument. 13 heavy-caliber Browning M2 machine guns, which gave it the name Flying Fortress. At peak production, in 1944, the Willow Run plant rolled out 1 B-17 bomber, every 63 minutes. Just think about that. Every hour, 24 hours a day, a brand new, battle-ready heavy bomber rolled through those factory gates. It was a non-stop river of steel, aluminum, and firepower. In total, during the war years, 3 companies, Boeing, Douglas, and Ford, built over 12,700 flying fortresses. This wasn't just a victory of technology, this was a victory of logistics, organization, and most importantly, people. 1.5 million ordinary Americans who put aside their peacetime lives and became soldiers on the industrial front. They proved that a free nation, when united by a common paycheck, is capable of genuine miracles. That was the arsenal of democracy in action. Thanks for watching. Hit that like button, subscribe, and see you next time. Imagine a metal that looks like a liquid, moves on its own, and for centuries was thought to be the key to immortality. What if this very substance drove scientists insane, killed entire cities, and still hides underground today, waiting for human error? Every year, the world produces and isolates thousands of tons of this stuff. But the real danger isn't in the numbers. It's that mercury never disappears. It migrates, it accumulates, it comes back. From alchemists who breathed in its vapors to tragedies born from normal water and fish, this is the story of a metal humanity called poison way too late. Stick around till the end, and you'll learn why even today, mercury isn't seen as a resource. It's a threat you can't just bury. In ancient civilizations, people knew about mercury long before they understood how dangerous it was. They found it in nature as cinnabar, a bright red mineral that released mercury when heated. Chinese alchemists thought it was an ingredient for immortality. Egyptians used it in rituals. Romans put it in mirrors and cosmetics. Spoiler, none of this ended well. But back then, nobody was reading safety labels. In medieval times, mercury became the star of alchemy. It symbolized change and transformation because it could be both metal and liquid at the same time. Alchemists believed it was the key to making gold. They breathed its vapors, touched it with bare hands, mixed it with other substances, and genuinely wondered why their hands were shaking, their memory was failing, and weird psychological symptoms were kicking in. That's how the mad scientist trope was born. No memes required, just real consequences. The modern era brought mercury an even bigger upgrade. It was used in thermometers, barometers, manometers, fluorescent lamps, batteries, switches, and even medicine. Yep, doctors once prescribed mercury as medication, for infections, even for bad moods. The biggest fail? Treating syphilis with mercury ointments. The disease might not go away, but poisoning was guaranteed. Who remembers mercury thermometers? Drop a comment if you've got one. It was in the 20th century that humanity started to collectively realize mercury wasn't just weird, it was genuinely dangerous. It's toxic in any form, but especially sneaky because it evaporates easily and builds up in your body. Nervous system damage, coordination problems, memory loss, vision issues. This isn't some thriller script, it's what chronic mercury exposure actually does. The phrase "mad as a hatter" didn't come out of nowhere. Hat makers used mercury compounds, and craftsmen literally lost their minds. Then there's the dark chapter of ecology. Mercury doesn't disappear, it migrates. When it hits water, it transforms into methylmercury and enters the food chain. Fish eaten by humans, and suddenly the toxins inside you. The tragedy of the Japanese city of Minamata became the symbol of this problem. Mass poisoning affecting thousands of people proved that a little mercury is a myth. In the mid-20th century, in the Japanese coastal city of Minamata, a chemical plant spent years dumping wastewater loaded with mercury compounds into the bay. The water looked normal. Fish were biting. Life went on, until people started getting mysteriously sick. First came the seizures, tremors, loss of coordination, speech problems. Then, paralysis, blindness, death. Mercury hit children especially hard. Infants were born with severe nervous system damage, even though their mothers often showed no obvious symptoms. The culprit was methyl mercury, accumulating in fish and shellfish, the foundation of the local diet. The toxin didn't disappear or dilute. It intensified at every level of the food chain. For decades, the company and authorities denied responsibility, while victims fought not just disease, but indifference. Minamata showed the world a simple, brutal truth. Even minimal doses of mercury can have catastrophic consequences when they become part of the environment. It was the end of the illusion of safe mercury. Mercury deposits exist today, but attitudes toward them are radically different from centuries past. The primary natural source of mercury remains cinnabar, a bright red mineral, mercury sulfide, which forms in hydrothermal deposits, often near volcanic zones, and fractures in the Earth's crust. It's from cinnabar that metallic mercury was historically obtained through roasting, and this process has remained virtually unchanged technologically. What changed were the scale and the regulations. The largest known mercury deposits in the 20th century were developed in Spain, Italy, China, Kyrgyzstan, Mexico, and Algeria. Spain's Almaden deposit was once considered the world's largest, and for centuries supplied a significant portion of global production. Today, it's basically mothballed, like most classic mercury mines. The reason's simple: demand tanked, and the environmental and health risks became too obvious to ignore. China remains the main mercury producer now, but even there, extraction volumes are way lower than in the past. Many countries aren't opening new deposits. They're working with existing stockpiles or secondary mercury recovered from industrial waste recycling and dismantling old equipment. The world has essentially shifted from active mining to a mode of control and reduction. Modern mercury deposits are increasingly viewed not as a future resource, but as a problem that needs to be safely isolated. Some deposits get shut down, others are reclassified as geological landmarks or monitoring sites. Mercury still sits deep within the planet's core, but its story as a strategic metal is nearly over. Now it's an element humanity handles with extreme caution. Underground mercury ore extraction in China typically starts with a narrow portal carved into rock, the entrance to a mine shaft. It might look like a dark rectangle in stone, reinforced with concrete or metal frames. Inside, a tunnel several yards wide, where small mining vehicles can pass through or conveyor belts can run. The working space is cramped and low. The ceiling's propped up with beams, the walls damp, streaked with reddish or dark brown veins of cinnabar. Lighting: cold fluorescent lamps casting harsh shadows. The air's heavy, so ventilation is critical. Along the tunnels run air ducts, humming and pushing fresh air deep into the mine, while simultaneously pulling out dust and gases. The ore itself is extracted using drill and blast or mechanical methods. First, drilling rigs bore a series of holes into the rock. It looks like rhythmic metal biting into stone. Then, if blasting is used, minimal charges are placed in these holes. The explosions are controlled, small. The goal isn't to destroy everything, but to peel away the rock. After that, the tunnel fills with dust that settles for minutes, while ventilation runs at full blast. Next, mechanization takes over. Front-end loaders rake up the broken rock, or gather it in buckets and dump it into mine cars or onto a belt conveyor. The stone looks uneven, with flecks of red. That's cinnabar, the main target. People try not to touch the ore with bare hands unless they have to. The dust is dangerous, so workers wear respirators, thick coveralls, gloves. How strictly this is enforced depends heavily on the specific operation. If it's a semi-underground or open-pit mine, the picture is different. There you'll see step-like benches cut into the rock where equipment moves around. Excavators strip away layers of ore, trucks haul it up to the surface. But even here they try to avoid huge open spaces, mercury dust and fumes, enemy number one, which is why open pits are less desirable for this kind of metal. All that ore doesn't sit around in the mine for long. It's immediately transported to the surface in sealed containers or on covered conveyors to minimize dust dispersal. At the mine exit, you'll often see washing stations, equipment, and sometimes the workers themselves get hosed down so they don't carry cinnabar particles beyond the production zone. After extraction, the ore is crushed and sent for heat treatment. Cinnabar is heated in specialized furnaces, where the mercury sulfide breaks down and the metal evaporates. This stage is the most dangerous. Mercury vapors are toxic, so modern facilities are equipped with sealing, condensation, and filtration systems. The vapors are cooled, after which the mercury transitions to a liquid state and is collected in sealed containers. Formally, all these processes are supposed to occur in a closed loop with no emissions into the environment. In practice, this is where the biggest questions arise. At large state-run or licensed operations, oversight is stricter. There's air monitoring, waste disposal protocols, and tracking of every kilogram of metal. At smaller or semi-legal operations, the risks are significantly higher, and these have historically been the source of local contamination and poisoning. They extract it in mountains where stone is born from flames and pressure capable of crushing anything alive. Its formation takes hundreds of millions of years, and today, people cut it with diamonds at a speed of 20 miles per hour. But what if I told you that this shiny material, used to decorate palaces and statues, was once the bottom of an ancient ocean, and that every slab of marble is a frozen story of life, death, and time? Watch until the end, and you will see how nature creates its own masterpiece, and people try to uncover its secret. Marble is not just a beautiful stone for decoration or sculpture. It is a material that has millions of years of geological transformation behind it. Its journey begins deep underground, where temperature and pressure change ordinary rocks beyond recognition. The basis of most marble is limestone, a sedimentary rock formed mainly from calcite. Limestone is formed at the bottom of ancient seas and oceans from the remains of marine organisms, corals, mollusks, foraminifera. Over millions of years, these fragments settle, compact, and cement together under pressure to form thick layers. When such layers fall into a zone of tectonic processes, where the Earth's crust moves, compresses, or subsides, they sink into deeper layers of the Earth. There, the temperature can exceed 1,200 degrees Fahrenheit, and the pressure reaches 1,000 atmospheres. Under these conditions, metamorphism begins, the process of transforming rocks without complete melting, but with a change in their structure. During metamorphism, the calcite crystals in the limestone begin to recrystallize. The old grains disappear, and instead, new ones grow, larger, tightly fused together. This process gradually transforms the loose sedimentary rock into a solid monolith with a characteristic shine and granular texture. It is this structure that gives marble its famous ability to be polished. The variety of colors and patterns in marble is the result of impurities that got into the limestone during its formation or metamorphism. If there is iron in the rock, the marble acquires reddish or yellow hues. Graphite or organic matter makes it gray or black. Impurities of serpentinite or chlorite add green tones. Quartz, dolomite, and pyrite create veins, the same patterns that make marble seem alive. Marble is not formed instantly. The process can take hundreds of millions of years. In places where tectonic plates collide, for example, in the Himalayas, the Alps, or the Apennine Peninsula, the rocks experience the most intense pressure. That is why such areas have become world centers for marble quarrying. For example, Carrara in Italy, where white marble of extraordinary purity was formed. During metamorphism, degassing also occurs, the release of carbon dioxide that remained in the pores of the limestone. Because of this, the structure of marble becomes almost non-porous. This density makes it durable, but also more brittle with sudden changes in temperature. In some cases, the process of marble formation can be partially reversible. If the temperature is too high, the calcite begins to melt, forming intermediate forms between metamorphic and igneous rocks. Such transitional marbles are found in areas of contact between limestone and magmatic intrusions, for example, near granite massifs. Another interesting feature is the zonation of formation. In nature, it is rare for an entire layer of marble to have the same structure. In different areas, the pressure and temperature are different, so some layers are coarse-grained, others are fine-grained, some have veins, others have a uniform color. This explains why even within a single quarry, marble of a completely different appearance can be extracted. When geologists study deposits, they are looking for precisely those places where the limestone has undergone complete metamorphism, but has not been destroyed by excess heat or deformation. Sometimes these layers lie at a depth of several hundred feet. Sometimes they come right to the surface, as in Tuscany or Greece. The quarrying and processing of marble is no less fascinating a process than its formation. The modern marble industry combines powerful machinery, precise laser technologies, and artisanal craftsmanship that has barely changed since the time of Michelangelo. The first stage is the identification of the deposit. Geologists conduct research on mountain ranges, using georadar, laser scanning, and drilling samples. The goal is to find a layer of marble of the required thickness, color, and uniformity. Sometimes the required layer lies almost on the surface, as in Carrara in Italy, or on the island of Paros in Greece. In other cases, it has to be uncovered, removing tens of feet of rock from above. When the site is prepared, the separation of marble blocks begins. Once, this was done with explosives, but now much more precise and safer methods are used. The main tool is diamond wire saws. This is a steel cable on which hundreds of diamond segments are strung. The cable is stretched between two pulleys and rotates at a speed of over 20 miles per hour, gradually cutting the stone like a string cuts cheese. Thanks to a water cooling system, the cut is even and smooth, without cracks. Another method is drilling vertical and horizontal holes in the rock, through which a diamond wire is then threaded. This forms the rectangular contour of the block. When the cuts are connected, a huge piece of marble, usually weighing from 20 to 50 tons, is separated from the mountain massif. It is propped up with hydraulic jacks, steel wedges are inserted, and the block is gradually released, preventing a sudden fall. Next, the blocks are transported from the quarry to processing plants. On the slopes of mountains, powerful tracked loaders and platforms on heavy trailers are often used for this. In mountainous areas where there are no roads, marble is sometimes lowered by special cable systems, a kind of funicular that leads from the quarry to the valley. In the workshops, the blocks are cut into slabs or blanks. For this, gang saws are used, large frame machines with dozens of steel blades, between which an abrasive mixture with water is fed. In modern production, they have been replaced by diamond circular saws, or laser cutting machines. The cutting accuracy reaches fractions of a millimeter. After cutting, the surface of the slabs is ground with abrasive stones of different grits, gradually moving from rough grinding to mirror polishing. If the marble is intended for architectural projects, it is further strengthened. A thin layer of resin or fiberglass is applied to the backside. This prevents chipping during transportation and installation. For sculptures, such reinforcement is not done. On the contrary, they look for a stone with a uniform texture without microcracks. Polishing is a separate art. It is performed on large machines where a series of round abrasive discs pass over the surface, gradually giving it a deep shine. To achieve a perfect effect, powders of tin or cerium oxide are used. It is they who reveal the structure of calcite, and the marble begins to play with reflected light. After polishing, the marble slabs are marked and sorted by color, pattern, and quality. Part of it is sent for export, another part to workshops for carving, facing, or manufacturing architectural details. Sculptors work with marble much more delicately. They use hand chisels, hammers, and now, pneumatic tools that allow them to carefully remove the stone layer by layer. Even with modern technologies, the art of marble processing remains semi-artisanal. It requires an eye, a touch, and an understanding of how the rock behaves. At the end, the marble products are coated with protective waxes or silicone impregnations, which enhance the shine and protect the surface from moisture. For interior work, softer compositions are used. For facades, water-repellent, UV-resistant ones. Quarries are usually located in mountainous areas that are difficult to reach. To cut blocks weighing from 20 to 50 tons, expensive equipment is needed: diamond wires, cranes, hydraulic jacks. At the same time, about 30 or 40% of the quarried stone is suitable for commercial use. The rest is cracked or defective blocks that go to waste or are crushed into crumb. Due to the mass and fragility of the slabs, they are transported on special trailers or containers with cushioning. For imported marble, delivery can account for up to 30% of the final price. Every 3 seconds worldwide, a new engine block rolls off the production line, the heart of a car that will withstand millions of explosions, temperatures over 4,600 degrees, and operate for decades without stopping. But how do you transform molten metal into a perfect mechanism with precision down to a micron? One mistaken dimension, and the engine will tear itself apart within minutes of operation. Every year, over 100 million of these blocks are manufactured, and each one goes through a hellish birthing process. Molten metal at 5,400 degrees, sand molds that self-destruct, and robots that cut channels thinner than a human hair. But there's one secret the manufacturers don't talk about. A mystery hidden inside every block that determines whether your car will go 60,000 miles or 600,000. Stay until the end. What you'll learn will forever change how you see what's happening under your car's hood. Let's start by understanding what an engine block actually is. It's the foundation that holds the entire engine together. Inside it are the cylinders where fuel combustion occurs, pistons that move up and down, and other critical components. The engine block must be strong, lightweight, and resistant to high temperatures. That's why manufacturing it is a complex process that demands precision and advanced technology. Everything begins with an idea. Engineers develop a concept for an engine that must be powerful, economical, and environmentally friendly. They use specialized 3D modeling software to create a digital model of the block. This allows them to account for every detail and test how the engine will perform under various conditions. Engine blocks are made from different materials, but the most common are cast iron and aluminum. Cast iron is strong and resistant to high temperatures, but heavy. Aluminum is lighter and dissipates heat better, but less durable. Sometimes composite materials or alloys are used to combine the advantages of both metals. After the engineering team completes all calculations, computer modeling, and finally approves the design of the new engine block, the true heart of the future automobile, the most interesting part begins: its birth in metal. The first and perhaps oldest step in metallurgy is casting. A massive shop filled with the hum of machinery, the smell of molten metal, and the glow of high temperatures. This is the foundry, where engineers' dreams become real components. First, a mold for the block is created. There are two main approaches to creating these molds, each with its own advantages. The first, and most common for large-scale production, uses sand molds. This is an amazing, though traditional method. First, they make a pattern of the future engine block, usually manufactured from wood or metal, and it's an exact copy of the block, but accounting for certain features, such as compensation for metal shrinkage during cooling. Then this pattern is placed in a special container, where it's tightly packed with a mixture of quartz, sand, clay, and organic binding agents. This mixture is compacted, then baked or chemically hardened, creating a strong but porous mold. After this, the pattern is carefully removed, leaving a cavity that precisely matches the shape of the future block. The most challenging aspect of sand molds is creating internal cavities, coolant channels, oil passages, cylinder bores. For this, they use so-called cores, separate elements, also made from sand, that are inserted into the mold. After pouring the metal and cooling, the sand is easily removed, leaving the necessary internal channels. The advantage of sand molds is their relative affordability per unit at large volumes and the ability to create very complex internal geometries. The second method, often used for aluminum blocks or smaller production runs, uses metal molds or permanent molds. These are stronger, reusable molds made from steel or cast iron. They're more durable and allow for parts with smoother surfaces and higher dimensional accuracy right from the casting stage. However, metal molds are much more expensive to manufacture, and it's harder to adapt them for creating the very complex internal channels found in engine blocks. Therefore, they're often combined with sand cores for internal cavities. The chosen material, cast iron or aluminum, is melted in a furnace at high temperature. For cast iron, this is typically over 4,600 degrees Fahrenheit. For aluminum, around 3,000 degrees. In massive induction or arc furnaces, metal scrap and pure ingots slowly transform into a glowing, liquid mass that shines bright orange or silvery light. This process includes precise control of chemical composition. Metallurgists add special alloying elements, such as silicon, magnesium, copper, in strict accordance with the recipe, to give the future block necessary properties: strength, wear resistance, lightness. The molten metal is constantly stirred and goes through refining processes to remove unwanted impurities that could reduce the quality of the finished part. Finally, the climax arrives: pouring. The molten metal, radiating intense heat, is carefully transferred from the furnace into special ladles, then into the prepared molds. This is the moment of maximum concentration and precision. The metal must fill every cavity of the mold, displacing air and completely matching its configuration. The pouring process can be gravitational, meaning the metal simply flows under gravity or under pressure, which ensures better mold filling and reduces porosity. After pouring, the mold remains for some time, so the metal can cool and solidify. This can take from several minutes to several hours, depending on the block size and metal type. When the metal has cooled and fully crystallized, the next stage occurs. The mold is broken apart. If it's a sand mold, it's simply destroyed using vibration or hydraulic hammers, freeing the newly created metal object. The sand is later collected and partially recycled. If it's a metal mold, it's opened and the finished block is carefully extracted. As a result of this process, we get what's called a rough engine block. It's not perfect yet. Its surface is rough, it may have sand residue or so-called flash, small metal overflows at the mold seams. It doesn't yet have mounting holes, and it lacks the micron tolerances required for engine operation. But it's already a real block. Massive and heavy if it's cast iron, or surprisingly light if aluminum, but already with a clearly defined shape, ready for the next processing stages that will transform it into a high-precision part capable of withstanding incredible loads inside the engine. Mechanical processing is performed on specialized computer numerically controlled machines. The large, solid block is secured on a special table. Around it, various tools move, performing their work. Like a scene from some movie, isn't it? Let's start with the most obvious: cylinder bores. These holes must be perfectly round, have precise diameter, and be positioned exactly on one axis, since pistons will move within them. First, machines use large end mills to roughly remove material, creating preliminary holes. It's like carving out a large chunk from cheese. Then more precise tools come into play. Special boring cutters are used, which carefully remove the thinnest layers of metal, bringing cylinder diameters to the required size. This happens in stages, with constant dimension control. After this, cylinder walls undergo honing. This is final abrasive processing that creates very fine, cross-hatched scratches on the internal surface. These scratches retain lubricant, ensuring perfect lubrication of piston rings and minimizing friction, which is critically important for engine efficiency and longevity. Actually, the cylinder surface after this processing feels perfectly smooth to the touch, but under a microscope has the perfect structure for retaining an oil film. Next, oil and cooling channels. These systems that penetrate the entire block are vitally important. Oil channels deliver lubricant to all moving engine parts, such as the crankshaft, camshaft, pistons, ensuring their lubrication and heat removal. Cooling channels circulate coolant, removing excess heat generated during fuel combustion and maintaining optimal engine operating temperature. The internal, complex labyrinths of coolant and oil channels, as we mentioned, are formed during the casting stage using sand cores. But after this, they need to be opened and brought to perfect condition. For this, high-precision drills and mills are used to create inlet and outlet openings for these channels, and also connect them with other engine parts. Each hole must be positioned with millimeter, or even micron precision, so fluids can circulate freely. There's a metal out there almost nobody ever sees. But it's what turns steel into armor. How is it that just a few grams of vanadium per ton can boost a structure's strength by tens of percent, and literally lighten the weight of the world? Where does this element hide if it's almost never found pure in nature? And why is it often extracted not from ore, but from dark slag that others consider waste? Today, you'll witness vanadium's journey. Hellish furnaces, blinding molten metal, fire-colored powder, and the birth of ferrovanadium that transforms steel in an instant. And at the end, I'll reveal why control over vanadium is no longer just metallurgy, it's geopolitics. Vanadium holds a special place among industrial metals, though for most people it remains nearly invisible. It's rarely seen in pure form, it's not used for jewelry, and it's barely associated with everyday life. Yet vanadium became one of the key factors in the creation of armored steels and modern high-strength structures, without which bridges, skyscrapers, automobiles, and heavy machinery would be impossible to imagine. The history of vanadium as a metal begins in the 19th century, but it gained real industrial significance much later, when metallurgists understood how even tiny amounts of this element could radically transform steel's properties. In nature, vanadium almost never occurs in its free state. Most of the time, it's found in complex minerals and ores, particularly vanadium-bearing titanomagnetites, and also in magnetite, where it replaces some of the iron atoms in the crystal lattice. The major vanadium ore deposits are concentrated in China, South Africa, Russia, and a few other countries. Mining is typically done through open pit or underground methods, depending on how deep the ore bodies lie. Magnetite ore with vanadium impurities goes through crushing and enrichment after extraction, where they separate out a concentrate with high iron and vanadium content. At this stage, the material isn't split into individual metals yet. It's a complex mixture of oxides. Vanadium's next stop, where metallurgy becomes a true industrial spectacle. Melting magnetite concentrate happens in blast furnaces or electric arc furnaces running at temperatures over 2700 degrees Fahrenheit. Inside the furnace, a mass of ore, coke, and fluxes slowly descends, passing through zones of different heat where solid chunks first sinter together, then transition into liquid. Molten iron collects at the bottom of the furnace, while lighter components, including vanadium oxides, concentrate in the upper slag layer. When the moment of release arrives, the furnace opens, and glowing streams pour out. Liquid slag glows with a blinding yellow-orange light, flows through channels, and throws up clouds of steam when it hits air or cooling surfaces. Right there in that seemingly spent mass lies the core treasure for vanadium production. After cooling, the slag transforms into solid, brittle chunks of dark material, deliberately collected and hauled away for further processing. Next up, crushing. Big pieces of slag pass through crushers and mills, getting ground into granular material or powder. The process hums with machinery, vibrations, and clouds of fine dust, immediately sucked away by filtration systems. The pulverized slag is prepped for chemical treatment, where vanadium needs to be extracted from an incredibly stable oxide matrix. Then the material enters reaction tanks filled with aqueous solutions of alkalis or salts. Under controlled temperature and constant stirring, leaching takes place. Vanadium compounds gradually transition into solution, shifting its color from pale yellow to rich orange or reddish. These visual changes directly indicate metal concentration and allow operators to monitor the process in real time. The resulting solution undergoes several purification stages. It's filtered, removing insoluble impurities, followed by precipitation, adding reagents that selectively bind vanadium. Inside the reaction vessels, a fine precipitate appears, gradually compacting and separating from the liquid. After washing and drying, this material becomes vanadium pentoxide, a bright powdery substance with a distinctive yellow-orange hue. From this moment on, vanadium stops being a hidden component in slag and becomes an independent industrial raw material. Vanadium pentoxide is then used to produce ferrovanadium, or is reduced to its metallic state. This entire sequence, from blinding molten metal to fine powder, vividly demonstrates how, deep within metallurgical processes, a material is born that defines the strength and reliability of modern steel. China produces 70,000 tons of vanadium annually, far exceeding the output of other countries and making it the global leader in both production and consumption of this metal. In terms of consumption, 90% of all vanadium goes into metallurgy, especially into high-strength microalloyed steels, where small additions of vanadium significantly increase mechanical strength, impact toughness, and fatigue resistance of structures. Ferrovanadium production is the critical link between chemical vanadium enrichment and the steel industry. It's in this alloy form that vanadium is most conveniently introduced into steel, precisely dosing its content and ensuring uniform distribution throughout the melt. The primary raw material for the process is vanadium pentoxide, obtained after processing slags or ores, along with metallic iron or iron-containing alloys. The process begins with charge preparation. Vanadium pentoxide is mixed with reducing agents, typically aluminum or silicon, and iron in strictly defined proportions. Next, the mixture is loaded into crucibles or electric furnaces, where conditions are created to reduce vanadium from its oxide state. Temperatures in the reaction zone reach over 3,600 degrees Fahrenheit, and it's at this moment that one of the most intense stages in the entire production line occurs. During aluminothermic or silicothermic reduction, the reaction proceeds extremely rapidly and releases a significant amount of heat. Vanadium oxides surrender their oxygen to the reducing agent, while pure vanadium transitions into a molten state and immediately dissolves in the iron. The result is liquid ferrovanadium with a specified metal content, typically ranging from 40 to 80% vanadium, depending on customer requirements. After the reaction completes, the melt is held to stabilize its composition, then poured into molds. As it cools, the ferrovanadium crystallizes, forming solid ingots or granules with a characteristic dark gray surface. The material is then crushed to a convenient size, packaged, and shipped to steel mills. The main value of ferrovanadium lies in its predictable behavior in molten steel. It dissolves quickly, is barely lost during melting, and allows precise control over microalloying. That's exactly why ferrovanadium became the standard form of vanadium supply for producing high-strength steels, from building structures to automotive components and armored products. The key feature of vanadium is that it works in microdoses. To get a noticeable effect, just tenths or even hundredths of a percent are enough. This means that for 1 ton of steel, only grams of vanadium are used, but those grams can boost yield strength, toughness, and durability by tens of percent. At the scale of millions of tons of steel, this delivers massive savings in metal, energy, and transportation costs. That's exactly why vanadium is often called the metal that lightens the weight of the world. Few people realize that vanadium also plays a role in long-term durability. Its compounds slow down grain growth at high temperatures and under repeated loading. This means structures made with vanadium steels age more slowly, handle cyclic loads better, and withstand sudden temperature swings. In real-world conditions, that translates to years of extra service life without repairs. Vanadium has become a critically important metal for infrastructure, and many countries have added it to their strategic materials lists. Control over vanadium flows means control over steel quality, and therefore over construction, transportation, and defense capabilities. This factor is increasingly shaping the geopolitics of metals. Every year, the world mines over 900,000 tons of rare earth metals, Without them, not a single smartphone, electric car, or wind turbine would work. But there's one place where most of them are born. Baiyun Obo, a massive quarry in the heart of China that supplies 70% of all the rare metals on the planet. Here, the earth glitters with metallic dust, and every dump truck hauls raw material for the future. But behind this shine hides a dark truth. Lakes of toxic waste, and the price nature pays for technological progress. Stick around till the end, and you'll discover how dust and poison create the foundation of modern civilization. The story of Baiyun Obo started back in the 1920s, when geologists discovered a strange ore in this area, a mix of iron and minerals unknown at the time. In the 1950s, Chinese scientists realized that hidden here was a treasure trove of rare metals: neodymium, praseodymium, cerium, yttrium, and lanthanum. Since then, Baiyun Obo has become the heart of China's strategy that would eventually turn the country into the undisputed leader of the global rare earth market. Every year, about 270,000 tons of rare earth concentrate are mined here, more than all other countries combined. It all starts simply. Massive dump trucks the height of a 2-story building pull up to the edge of the quarry, where giant excavators with buckets like a dinosaur's mouth rip out chunks of monzonite ore. Each bucket can hold over 100 tons. The dust rises in columns, and it feels like the very air here is saturated with metal. But extracting the ore is just the beginning. The real value is hidden in microscopic inclusions of rare earth minerals. Their share in the rock is only a few %, so after extraction, the ore is crushed and sent to processing plants, where a complex chemical story begins. First, the ore is ground to dust, then subjected to flotation, a process where particles suspended in water are separated using reagents. Rare earth particles stick to air bubbles, rise to the top, while the rest settles to the bottom. This is just the first step, because the concentrate still contains plenty of impurities: iron, calcium, fluorine. Next comes chemical extraction, which transforms the concentrate into high-purity oxides. This is an extremely complex process. In specialized reactors, the ore is treated with acids, usually sulfuric or hydrochloric, sometimes with the addition of fluoride compounds. After this, the resulting solution is separated into fractions using organic solvents. Each element, neodymium, praseodymium, cerium, has its own chemical quirks, so the process requires dozens of sequential cycles of extraction, precipitation, filtration, and drying. It's these oxides that then go into the production of permanent magnets, the main consumer of rare earth metals. For example, one iPhone might contain less than 1/10,000th of an ounce of neodymium in the speakers and vibration motor. In a modern wind turbine, nearly 1,400 pounds of this element. And here's the wow fact: just 1 gram of neodymium can provide a magnet for a turbine that generates electricity for roughly 1,000 homes. It sounds like an energy miracle, but it has a flip side. The problem is that chemical processing of rare earth ores is extremely toxic. Every gram of pure metal means tons of waste. In the Baotou area, near Baiyun Obo, real waste lakes have formed. Black, acidic bodies of water where radioactive elements, fluorides, and heavy metals accumulate. They're visible even from satellite. Even with modern cleaning technologies, chemical processes leave their mark on the environment. Local residents tell stories that, over the past decades, dust from the quarry and processing plants has changed the soil color, and grass around the area has been growing worse. However, the Chinese government is taking measures, implementing closed-loop water systems, controlling acidic runoff, and converting some facilities to new, green technologies, where instead of traditional acids, they use ionic solutions and membrane separation. All this is being done not just for environmental reasons, but also because China aims to maintain its dominance in the global rare earth metals market. Today, it accounts for 70% of global production and over 90% of finished oxide and magnet production. Other countries, the US, Australia, Vietnam, Malaysia, are trying to develop their own deposits, but they haven't come close to Chinese scales yet. Baiyun Obo has become more than just a quarry. It's a symbol of the technological era, where Earth transforms into smartphones and ore becomes electric wind. Right here, among mountains of metallic dust, the elements that power digital civilization are born. There's a certain irony in this. In the quest to create a green future, humanity has become dependent on one of the dirtiest industries. Magnets for electric cars and turbines, batteries, solar panels. All of this requires metals extracted from places like Baiyun Obo. And the greater the demand for clean energy grows, the deeper this giant wound in the earth becomes. Despite this, for China, Baiyun Obo is a source of national pride. Thousands of people work here, and the territory itself is equipped with modern infrastructure. Conveyor systems, automated drilling rigs, chemical plants that operate almost without human involvement. On the surface, sensors are installed that track air composition, and in reservoirs, pollution levels are monitored in real time. Every dump truck descending into the quarry is part of a giant machine that supplies the world with energy, data, and sound. And when we hold a lightweight smartphone in our hands, it's worth remembering that a piece of this device, maybe even that very magnet in the speaker, was once dust in the Mongolian desert. Neodymium is one of the most famous, and at the same time, most mysterious rare earth metals. It's a silvery white, shiny, fairly soft metal that easily oxidizes in air, so it's usually stored under a layer of oil, or in an inert atmosphere. Sounds unremarkable, but this element has become the quiet engine of the modern technological revolution. Without neodymium, wind turbines, electric cars, headphones, laptops, and even rockets wouldn't work. In pure form, neodymium doesn't have the magnetic properties it's valued for. They appear when it's combined with iron and boron, forming an alloy. This is the material used to make the most powerful permanent magnets on Earth. One neodymium magnet can hold weight hundreds of times its own. In industry, it's called a supermagnet, and for good reason. It's what makes compact electric motors, miniature speakers, and highly efficient generators possible. One study indicates that between 2001 and 2021, Baiyun Obo supplied about 60% of neodymium from China's total neodymium extraction. On one hand, Baiyun Obo is a remote, harsh, and dusty place. On the other, it evokes an almost magnetic curiosity in those who want to see what modern civilization looks like in its raw material form. Baiyun Obo today is not just a mine, but an entire complex with its own small town, a rare earth elements museum, and even a special viewing platform from which you can see the giant pit going hundreds of feet deep. The flow of tourists here is small by Chinese standards, but steady. These are mainly engineers, geology students, bloggers, eco-tourists, and those fascinated by industrial landscapes. In 2019, local authorities even declared Baiyun Obo part of the Industrial Heritage of Inner Mongolia route to show how mining and processing have transformed the region. In tourist brochures, this place is called the heart of the rare earth planet. The road to the quarry leads through endless plains and low hills, where the wind almost never stops. The air carries the smell of metal, and from a distance, the quarry looks like a giant amphitheater, where Earth plays the starring role. Tourists aren't allowed close to the mining zone. It's too dangerous, but there are several safe spots from which you can take photos. The most striking moment is when quarry dump trucks slowly move at the bottom of the pit. They look like toys. The scale is so massive. 70% of the plastic you toss in the recycling bin ends up straight in a landfill. Not because you're doing something wrong, but because traditional recycling only wants clean, single-type plastic. Everything else, dirty packaging, films, toys, shoe soles, not its problem. But there's a technology that takes any dirty, mixed plastic and turns it back into oil. No burning, no oxygen. I just visited one of only 25 facilities like this in the entire world, and I'm going to break down exactly how it works. From a pile of trash to a barrel of synthetic oil. Plus, one number from the director that makes it crystal clear. Even this is just a drop in the ocean. Regular plastic recycling, the kind you know from those triangle bins, it's super picky. It wants plastic to be one type, clean, no caps, no labels, no food residue. Plastic bottles, separate. Polyethylene, separate. Polystyrene, they often refuse to take it at all. And anything that doesn't meet these criteria, which is roughly 70% of all plastic that ends up in the trash, goes straight to the landfill, or gets burned. All that dirty food plastic, multi-layer chip bags, toys, shoe soles, films, traditional recycling doesn't want them. And that's where a different game begins. What they do at this facility is called chemical recycling, or plastic pyrolysis. And the principle is so simple, at first you don't even believe it. They take plastic and heat it without oxygen to temperatures between 550 and 900 degrees Fahrenheit. At that temperature, the long polymer chains. And plastic, if we're being brief, is just very long chemical chains, break apart into short fragments. These fragments escape as vapor, enter a condenser, cool down, and turn into liquid. This liquid is pyrolysis oil, or synthetic crude oil. The exact same product that's the starting point for making plastic, gasoline, chemicals. The circle is complete. But the gap between theory and what happens here in practice? Wide as Texas. First problem, raw materials. The plant processes anywhere from 150 to 200 tons of mixed plastic every single day. I saw this pile. It looks like where all your plastic bags, disposable lids, and thermos caps go to die. Before any of this hits the reactor, it goes through sorting, cameras, magnets, air separators. Metal has to come out completely because it just won't break down in the reactor and it clogs the equipment. Chlorinated plastics, for example, have to be separated out because when heated, they release hydrogen chloride, which literally eats the reactor from the inside. One poorly sorted container can shut down the entire line for days and cost the plant tens of thousands of dollars in repairs. After sorting, the plastic gets cut into pieces roughly 1 inch by 1 inch. This ensures even heating in the reactor. The shredders here are the size of a bus and chew through everything with a sound that makes you want to jam in earplugs and drive home. Then these pieces get fed into the reactor by an auger conveyor. The reactor, that's the key piece, and all the complexity revolves around it. It's a massive steel cylinder. This facility has 6 of them, each as tall as a 3-story building, and inside, a complete absence of oxygen is maintained. This is critical. If oxygen gets in at these temperatures, you won't get pyrolysis, you'll get ordinary combustion. Basically, a fire inside. That's why before feeding in the plastic, the system is purged with nitrogen, replacing the air with an inert gas. Oxygen sensors are mounted on every flange, and if the level rises above 0.5%, the line shuts down automatically. At 750 degrees Fahrenheit, polymer chains start breaking apart. Polyethylene, polypropylene, polystyrene, they all have different cracking temperatures, different reaction rates, different product yields. That's exactly why mixed plastic is so tricky. If you fed only pure polyethylene into the reactor, you'd get a stable 80% oil yield by weight of feedstock. With mixed plastic, that number bounces between 50 and 65% depending on batch composition. And there's no way to predict more accurately without chemical analysis of every ton. And that kind of analysis costs money. Real money. The vapor coming out of the reactor is a mixture of hydrocarbons of different sizes. It passes through a fractionation column where it separates by boiling point, almost like at a regular oil refinery. The lightest fractions are gases. They don't condense and get burned immediately in a burner to produce heat that's fed back into the reactor. At this stage, the plant is practically energy self-sufficient. It heats itself with its own gases. The middle fractions remain as pyrolysis oil, a dark, slightly viscous liquid that smells roughly like you threw a plastic bottle on a campfire and let it burn completely. The heavy fractions settle out as fuel oil or a waxy substance. And there's still a solid residue left over, carbon black or technical carbon. It gets pressed into pellets and sold to manufacturers of rubber products or pigments. There's another technical hurdle worth explaining: chlorine. Chlorine actually hides in a ton of different packaging, in dyes, additives, adhesives. When plastic with chlorine gets into the reactor, the chlorine reacts with water and forms hydrogen chloride, an extremely aggressive acid. It eats through the steel reactor walls from the inside in about 6 to 12 months instead of the projected 10 to 15 years. Replacing a single reactor costs several $1,000s and weeks of downtime for the entire production line. So chemical analysis of incoming plastic and chlorine monitoring is literally a matter of plant survival. While I was walking through the facility, one detail struck me: sensors everywhere. On every pipe, every valve, every welded joint, there are sensors for temperature, pressure, and gas composition. This entire system feeds into a central control room where 3 operators watch screens displaying roughly 300 parameters simultaneously. If pressure in any reactor jumps above the calculated value by more than 5%, an automatic valve releases the excess. If temperature drops below 2.5 degrees, cracking quality decreases and the oil comes out heavier. That's bad. If the temperature exceeds 900 degrees, gasification kicks in. Oil yield drops to 0, and all you get is gas and carbon. The window between normal and something went wrong? Literally 50 degrees. In a reactor the size of a house. The pyrolysis oil produced here gets shipped in tankers to petroleum refineries, where it's blended with regular crude and goes through cracking, turning into naphthene and xylene, which are feedstocks for making new plastic. So theoretically, a shampoo bottle could circle back to polypropylene pellets and become a new bottle. Some major chemical companies, including several from the global top 10, are already buying this oil to manufacture plastic, and even paying a premium over conventional petrochemical feedstock, because they can print "made from recycled plastic" on the packaging, and for them, that's a marketing asset. The plant director told me straight up that even if they double their capacity and hit 400 tons a day, they'll be processing less than 0.1% of the world's plastic waste stream. The solution to the problem? Either drastically cut plastic production or build several thousand of these plants across the globe. Right now, neither is anywhere on the horizon. But this plant is proof that mixed plastic pyrolysis technology can actually work at industrial scale and turn a profit, even if it's razor-thin margins with really nerve-wracking logistics. I'm walking out of here with respect for the people doing this work, and a solid sense that 92%? That number's going to stay relevant for a long time. And you know what else is going to stay relevant? Subscribing to my channel. What if I told you that a high-speed train wheel experiences temperatures hot enough to make metal glow, and still can't afford to fail? Why must this piece of steel withstand tests that would destroy any car wheel in seconds? There's a reason almost nobody suspects, and if you stay with me through to the finale, you'll discover the secret process that forces the wheel to survive where other metal simply melts. But first, tell me, does your country actually manufacture railway wheels, or are they imported? A train rockets down the tracks at over 186 miles per hour. At that speed, an ordinary wheel would simply disintegrate. Why? Because it has to withstand not just weight, but a whole series of inhuman trials. The material is everything. This isn't ordinary steel used for silverware or even car bodies. High-speed train wheels are made from a special grade of steel, melted according to a unique, meticulously refined recipe. This recipe is a combination of iron with specific alloying elements, manganese, silicon, chromium, molybdenum, that give the steel extraordinary strength, toughness, the ability to absorb impacts without failing, and endurance. Beyond that, this steel must be as pure as possible, free of any foreign impurities that could become a weak point. After the special steel is melted in massive metallurgical furnaces, it's poured into molds to create large steel billets, what we call slabs or blooms. But that's just the beginning. The real transformation starts in the forging shop. This is where one of the most powerful forging presses comes into play, along with specialized forging machines. The billet, heated until it glows bright yellow or red, that's around 2000 degrees Fahrenheit, is fed under the press. The process involves multi-stage forging. It's not a single strike, but rather a whole series of controlled pressures and rotations. The giant hammers, or jaws of the press, slowly, yet with unstoppable force, flatten and shape the red-hot metal. First stage, the billet is compressed to give it a rough circular shape, densifying the metal and eliminating internal voids. Second stage, the material is flattened and rolled, forming a disc with a central hole. This is where the future wheel's outline begins to emerge, with its rim, disc, and hub. This directional metal flow shapes its internal fibrous structure, making the wheel exceptionally strong in the required directions. Forging, unlike casting, transforms steel's microstructure. It compresses the metal's grains, eliminates casting defects, and creates a directional fibrous structure that gives the wheel exceptional strength and fatigue resistance. It's like an athlete's muscles. After training, they become stronger and more resilient. Why such complexity? Because high-speed train wheels operate under extreme conditions that are hard to imagine. When moving at speeds over 186 miles per hour, the wheel's surface heats up from friction against the rails and brake pads to nearly 2000 degrees Fahrenheit. That's the temperature at which metal begins to glow red and change its properties. And this heating isn't constant, it's cyclical. Heating during acceleration and braking, cooling during movement. The material must withstand these constant temperature fluctuations without forming microcracks, which over time can lead to failure. Each pair of wheels carries a load of dozens of tons. A single railcar can weigh between 50 and 70 tons, and this weight is distributed across just 4 wheels, that is, 2 wheel sets. This creates constant pressure acting on the wheel. The train doesn't ride on a perfectly smooth surface. It crosses rail joints, uneven sections, and switches, which generate continuous impact loads. The wheel must be incredibly tough to absorb these shocks without cracking or breaking apart. After forging, the wheels aren't finished yet. They undergo complex heat treatment, which is key to developing their final properties. The wheel centers, the discs that connect the hub to the rim, are hardened. Hardening is a process of heating steel to high temperatures, then rapidly cooling it. This makes the metal harder and stronger. But hardening makes the metal brittle, so it's always followed by tempering, reheating to a lower temperature with slow cooling. Tempering reduces brittleness and improves toughness while maintaining high strength. This combination of hardening and tempering creates the ideal steel microstructure that can withstand extreme operating conditions. But even after all these complex processes, no wheel reaches the rails without brutal yet necessary testing. Every single wheel, without exception, undergoes ruthless inspections. Ultrasonic testing. It's like medical ultrasound diagnostics, but for metal. Special sensors send high-frequency ultrasonic waves through the wheel. If there's even a microscopic crack, void, or defect inside, the ultrasonic wave bounces off it and creates an echo that the instrument captures. This method allows us to see internal defects without destroying the wheels. A defect the thickness of a human hair is already grounds for rejection. Magnetic particle inspection. The wheel gets magnetized, then its surface is coated with fine ferromagnetic powder. If there's a crack, even one invisible to the naked eye, it distorts the magnetic field, and the powder concentrates along that crack, making it visible. This reveals even the tiniest surface defects that could become failure points during operation. Only wheels with perfect structure and zero defects are cleared for installation on high-speed trains. This isn't engineering perfectionism. It's about the safety of thousands of passengers who trust their lives to these metal giants. While the United States isn't leading high-speed rail development like China or Japan, its rail network remains one of the world's largest, and American manufacturers have extensive experience producing high-quality wheels for various rolling stock, passenger trains, freight locomotives, and switching equipment alike. Unlike the automotive industry, where thousands of companies manufacture parts, the railroad wheel manufacturing market in the US is significantly more concentrated. This is a highly specialized field, requiring massive investments in metallurgical equipment, forging presses, and quality control systems. The two main and most powerful players in the North American railroad wheel manufacturing market are Amstead Rail and KF USA. While KF is a Spanish company, it maintains production facilities in the United States to meet local demand. Previously, other major manufacturers existed, but the market has consolidated. Total annual railroad wheel production in the US fluctuates, but can be estimated in the range of 300,000 to 500,000 units per year. This figure includes wheels for all types of rolling stock. It's worth noting that while the US can manufacture wheels capable of withstanding high speeds, the actual demand for wheels designed for continuous operation above 186 miles per hour remains relatively limited due to the scarce number of true high-speed rail lines in the country. For instance, Amtrak's Acela Express trains, running along the Northeast Corridor, reach speeds up to 150 miles per hour on certain segments, but not beyond the aforementioned threshold of 186 miles per hour, which requires specific material and design standards. However, US wheel manufacturing technologies and standards do enable production that meets international requirements for high-speed trains should the need arise. From a material standpoint, American manufacturers, like their global counterparts, utilize specialized grades of carbon steel alloyed with manganese, silicon, and other elements to achieve the necessary strength, wear resistance, and toughness. Forging, heat treatment, and non-destructive testing processes are standard and comply with the highest international safety and quality benchmarks. Every year around the world, billions of tons of rock are blasted apart with explosives. Tunnels are carved straight through mountains, and rockets are launched into the sky. But few have ever seen the place where the force capable of reshaping landscapes in seconds is born. Today, we gained access to one of the most tightly guarded industrial facilities, where chemistry, fire, and metal come together to create the legendary TNT, the very substance whose explosive power became the world standard. But the scariest and most fascinating part isn't the explosion itself. It's how this yellow powder makes its journey from an ordinary liquid to a material that can obliterate a house-sized boulder. And trust me, if you stick around until the end, you'll learn a fact about TNT production that will completely change how you see modern industry. TNT, or trinitrotoluene as it's also called, showed up way back in the 18th century, when chemists started messing around with toluene. Americans call it TNT, short for trinitrotoluene, and to this day, it's the gold standard. 1 gram of TNT, the unit for measuring explosive force. Here at the plant, everything starts with massive tanks of toluene. This liquid flows into reactors, giant stainless steel vessels, where the temperature holds steady at 400 to 480 degrees Fahrenheit. No, seriously, it's hell in there. 200 to 250 degrees Celsius if you convert it. A mixture of nitric and sulfuric acids gets pumped inside. Concentrates so harsh, they'll melt your gloves right off. The nitration process runs anywhere from 3 hours to several days. First you get mononitrotoluene, then dinitrotoluene, and finally trinitro. The acids circulate in a closed loop. They get recycled instead of just dumping them into the ground. Operators in protective gear monitor the gauges, pressure, temperature, concentration. Everything's under control because the slightest shift and the reaction can go sideways. From the reactor, the mixture heads to coolers, long coiled tubes where the hot TNT crystallizes. Then settling tanks. The heavy TNT sinks to the bottom, while the lighter acids get drained off. That jelly-like mass right there, that's raw TNT, still wet with acid. They wash it with hot water at 150 to 180 degrees Fahrenheit to neutralize what's left. The water drains into the sewage system, and the crystals get dried in vacuum ovens, rotating drums that spin like washing machines. Massive stainless steel vats get pumped full of water at temperatures between 150 and 180 degrees Fahrenheit. The water jets out like in an industrial laundry, washing away residual nitric and sulfuric acid. TNT floats in it like jelly in boiling water, spinning, giving up impurities. The process takes half an hour. The water changes 3 times because the first batch is yellow from acid, the second is cloudy, and the third is already clear as a tear. This water doesn't just go down the drain. It gets neutralized with lime in basins, filtered through a 10-foot thick layer of sand, and then released into the river. Ecology stays under control because acid is poison for fish. Meanwhile, the crystals get unloaded. The mass becomes solid, but still 6 to 10% wet. Now comes the drying, the most interesting part. The entrance to this vacuum oven, a room where 20 rotary drums hum, each about 6 feet in diameter. TNT gets shoveled in there, 200 pounds at a time. The drum seals shut. Air pumps out until pressure drops to 100 millimeters of mercury, and heating kicks in, 130 to 140 degrees Fahrenheit. Fans blast hot air through the center. The drum spins at 30 rotations per minute, like a washing machine on spin cycle. Crystals tumble, dry evenly, don't stick to the walls. 2 hours, and the doors swing open. Pure yellow powder, temperature 40 degrees, moisture content 0.5%. A worker in a mask pours it into hoppers, where a conveyor will carry it off to granulation. 5 tons per shift from one drum, and no dust because the vacuum pulls everything into filters. The operator jokes, "Dry as my sense of humor." Without this step, TNT would clump together or detonate from moisture. An hour or two, and we've got pure yellow powder. Color? Light yellow to dark orange, depends on purity. Here we get the top grade, 98% pure product. Next up, granulation. The powder gets moistened, pressed into briquettes the size of a matchbox, then crushed down to granules 2 or 5 thousandths of an inch in diameter. Why granules? Because the powder's easier to pack, doesn't create dust, and detonates evenly. I peer into the press, a giant machine with pistons pushing 200 atmospheres of pressure, and the briquettes come out hard as rock. Then the grinders, hammer mills where the shafts spin at 6,000 revolutions per minute. Dust gets vacuumed out by ventilation, because breathing in TNT, that's gonna cost you. Now packaging. Granules pour into airtight cardboard boxes weighing 100 pounds each. That's the standard for quarries and the military. Every box gets checked for moisture. No more than 0.70%, otherwise the TNT sweats and becomes sensitive. There are also barrel forms for underwater blasts. There the granules get mixed with paraffin so they don't get wet. Boxes are sealed, marked by lot, and done. Off to the warehouse. From here, TNT ships out to quarries, mines, defense. One box is enough to blast through 200 tons of rock. And then there's friction sensitivity. The cylinder spins for 6 hours, and if it doesn't blow, we're good. Lab techs in masks check purity with a chromatograph. Toluene or acid impurities aren't allowed. Nothing but respect. These people handle explosives like jewelers. Production is massive. 1,000 tons a month, that's millions of pounds. Energy? Electricity from gas turbines, steam from their own boilers. Waste. Acids get regenerated. Toluene gets redistilled. Environment? Filters on a 200-foot smokestack. Wastewater treated until it's clear. Neighbors don't complain. The plant sits 10 miles from the nearest town. Fun fact, TNT doesn't just explode. They melt it at 82 degrees Celsius, 250 Fahrenheit, and pour it into shells like hot wax, or mix it with gunpowder for plastic charges. In quarries, 1 ton can shatter rock the size of a 3-story building. In mining, you can't punch through a mile-long tunnel without it. And in the military, it's the backbone of torpedoes, mines, bombs. You know how much steel came into this plant? Thousands of tons. Reactors made of chrome molybdenum steel, because regular steel just gets eaten alive by acids. I'm standing in the granulation shop right now. Hear that press rumbling? See those granules pouring into bins like golden sand? The air's clean, but it smells like nitrocellulose. Familiar scent if you've ever been to a powder plant. The operator laughs. Don't breathe too deep, or you'll detonate yourself. Joking, obviously. But the discipline? Ironclad. 8-hour shifts. Lunch break with the clatter of spoons on metal trays. Compare that to the old plants. Back then, everything by hand. Women in skirts packing TNT with bare hands. Explosions once a month. Now, robotic arms, sensors, cameras. Evolution. One worker monitors 10 processes from a control panel. And the pay? Competitive. The plant's like a living organism, roaring, churning, producing power. TNT isn't evil, it's a tool. Builds roads, digs mines, defends the country. Without it, no 1,000-foot bridges, no tunnels under mountains. What if the metal that still powers most cars on the planet has been quietly poisoning people since the days of the Roman Empire? And we found out too late. Lead built aqueducts, adorned the faces of Egyptians, and today hides in billions of lead-acid batteries, without which cars, elevators, and entire cities would grind to a halt. We'll descend into mines where explosives shatter rock, trace the journey of galena to red-hot furnaces, and discover why this metal simultaneously saves infrastructure and destroys health. Stick around till the end. One fact about lead will forever change how you look at an ordinary battery. Okay, let's rewind the clock and dive into a story that began long before the first smartphones and even before the invention of the wheel. How did people even learn about lead, this sneaky, two-faced metal? Truth is, nobody knows exactly who or when first discovered lead, because it wasn't officially discovered by a scientist in a lab like many other elements. Lead is one of those metals that's just always been around humans, and its history is intertwined with the history of civilizations themselves. Picture this: ancient times, way before people learned to work with iron, or even copper. They were searching for interesting stones, clay, anything they could use. And then, in certain places, especially where there are ore deposits, they stumbled upon a really unusual stone. These were lead ores, most commonly galena, lead sulfide, which looks like dark gray, almost black crystals with a metallic shine, often in cubic shapes. Lead ores often lay close to the Earth's surface, and there was plenty of it around. Plus, lead sometimes occurs in its natural, pure form, though that's pretty rare. Lead has an incredibly low melting point, just 621 degrees Fahrenheit. This means you didn't need some super high-tech furnace to melt it down. A good hot campfire was enough, and if there happened to be lead ore nearby, shiny liquid metal could literally just melt right out of it. The metal in the ore heats up, melts, and starts flowing out of the rock, forming little shiny puddles or droplets. This must have been absolutely mind-blowing to witness. Out of stone, without any tools, just from fire alone, this shiny, heavy, soft material appears that you can shape with your hands. You could easily flatten it, bend it, cut it even with primitive tools. It wouldn't break like stone. This made it perfect for crafting simple objects. Archaeological findings show that lead was used as far back as 7,000 or 8,000 years ago, dating to the Neolithic period, for example, in Turkey. People found beads and other small lead objects there. In Mesopotamia, Egypt, and later in Greece and Rome, lead became widespread due to its availability and ease of working with. The Romans built their famous aqueducts and water supply systems using lead pipes. The word plumbing comes from the Latin plumbum, which means lead. Ancient Egyptians used lead sulfide for eye makeup, while Romans used it for skin lightening and in paints. Nobody back then, of course, suspected this metal was toxic. After all, lead poisoning symptoms were often chronic, developed slowly, and could easily be blamed on bad luck, other illnesses, or curses. People just saw a shiny, useful metal that was easy to work with, and they actively used it, never suspecting that beneath its appeal lurked a treacherous enemy. Now that we know the grim history of lead's discovery, let's fast forward to our time. Despite all its toxicity and the massive campaign to phase it out, lead is still part of modern industry. But how is it mined now, and where does it hide when we're so desperate to get rid of it? This is a story about precision, control, and the constant battle against its poisonous nature. Lead, like its neighbor zinc, is rarely found in its pure form. It's mostly extracted from ores, where it exists as lead sulfide, known as galena. And, as you might have already guessed, this anti-hero often shares its deposits with zinc, as well as other valuable metals like silver and copper. The world's top lead producers are China, Australia, the United States, and Peru, which once again overlaps with the geography of zinc mining. The extraction process starts with locating ore bodies. Geologists, armed with cutting-edge technology, scan the ground and conduct exploratory drilling to find spots where galena concentrations make economic sense. Once a deposit is identified, mining operations begin. This can either be an open-pit mine, where massive excavators strip away the top layers of earth, gradually working their way down to the ore, or an underground mine, where miles of tunnels are drilled, penetrating deep into the Earth's crust. In underground mines, drilling rigs are used to create holes in the rock, which are then packed with explosives. After controlled blasts that break up the ore vein, specialized loaders gather the ore fragments and haul them to the hoisting shafts. Ventilation systems run at full capacity, removing dust and pumping fresh air down into the depths. All the ore is brought to the surface, where it begins its long journey to becoming a metal ingot. After crushing, the flotation process kicks in. This is a chemical-physical method that separates different minerals. The crushed ore is mixed with water and special reagents in massive tanks. These reagents selectively attach to galena particles, making them water-repellent. Then air is pumped through the mixture, creating bubbles that the lead mineral particles cling to and rise to the surface as foam. This foam is collected, forming lead concentrate. The waste rock settles at the bottom and gets disposed of. Since lead and zinc are often found together, different reagents and flotation cycles can be used to separate them individually, which requires high precision and chemical control. The resulting lead concentrate, now containing a much higher percentage of lead, is shipped to the metallurgical plant. This is where it transforms into pure metal. The most common method is pyrometallurgy, which involves several stages. First, the concentrate is roasted in special furnaces at high temperatures. This is a calcination process that removes sulfur from galena, converting it into lead oxide. The sulfur that's released as sulfur dioxide gas is carefully captured and converted into sulfuric acid to prevent air pollution. Then the lead oxide is loaded into large blast furnaces, where it's mixed with coke and fluxes. In these furnaces, at temperatures over 2,000 degrees Fahrenheit, a reduction process takes place. The carbon from the coke pulls oxygen away from the lead oxide, releasing liquid metallic lead. The molten lead, which is extremely heavy, settles to the bottom of the furnace. On top, a layer of slag forms. That's the melted impurities. Molten lead is periodically drained from the furnace, but this isn't pure lead yet. It contains impurities of other metals, such as copper, silver, gold, bismuth, and nickel. That's why lead goes through one more stage, refining. This could be heating to specific temperatures to remove impurities, or electrolytic refining, where electric current separates lead from other metals, achieving very high purity. It's at this stage that valuable byproduct metals like silver and gold, which accumulate in lead ores, are extracted. So where is all this carefully mined and refined lead being used today, now that we know about its dangers? The biggest consumer of lead, accounting for about 85% of all global consumption, is the production of lead-acid batteries. These are the same batteries that start the engines in nearly every car on the road, and they're also used in uninterruptible power supplies, backup power for telecom networks, and large-scale energy storage systems. In electric vehicles, even though the main battery is lithium-ion, there's often still a small 12-watt lead-acid battery to power the onboard electronics. This is a massive market that keeps demand for lead rock solid. Without this unassuming rock, often mistaken for ordinary dark pebbles or heavy chunks of granite, modern electronics would instantly collapse into a pile of useless plastic and silicon. Tin ore, or more precisely its primary mineral, cassiterite, is the hidden foundation holding up our entire digital world. When we talk about high-tech, we name-drop gold or complex semiconductors, but this is the invisible glue binding billions of microscopic components into a single working system. Tin's journey begins deep in the planet's crust, where for millions of years, metal-rich solutions seeped into fractures in the earth, forming deposits that today drive the pace of human progress. Cassiterite, often called tinstone, has an incredible density and a distinctive diamond-like luster when fractured, though on the outside, it can look like ordinary brown or black rock. Mining this ore demands massive effort and specialized knowledge. The world's major reserves are concentrated in what's called the Tin Belt, stretching through Southeast Asia, China, Latin America, and Africa. The scale of extraction is staggering in its variety, from colossal open-pit mines and underground shafts to dredging operations on the ocean shelf. For example, off the coast of Indonesia, giant floating dredge factories pull up thousands of tons of tin-bearing sand from the seafloor, sifting it through complex filter systems to separate out the heavy ore particles. The process of transforming rock into pure metal is long and exhausting. Since tin content in ore is now low, the rock first undergoes multi-stage enrichment. It's crushed, washed, and separated using gravity methods that exploit cassiterite's high specific gravity. After obtaining the concentrate, the smelting stage begins in a furnace at around 2,200 degrees Fahrenheit. Here, under the influence of reducing agents, tin separates from oxygen and other impurities, transforming into a liquid silvery metal. But for the electronics industry's needs, this purity isn't enough. The metal goes through a series of refining processes to eliminate the tiniest traces of iron, copper, arsenic, or antimony. Only after this does it become the material we see in the form of solder. Solder. That's the main use for tin in the modern world. It's not just some auxiliary material. It's a critically important component of any electronic device. Previously, soldering used an alloy of tin with lead, but due to environmental requirements and health safety concerns, the world switched to lead-free technologies. Today, the latest circuit boards are joined using alloys where tin makes up 95 or even 99%. Every smartphone, laptop, control unit in cars, or satellite onboard computer contains several thousand soldered connections. Without tin's ability to wet the surfaces of other metals and create reliable electrical contact at low temperatures, mass production of electronics would be impossible. Factories that produce modern electronics operate with incredible precision, and that's where a key tool comes into play. In surface mount assembly shops, specialized machines deposit solder paste through stencils onto circuit boards with accuracy down to the micron. Then the board passes through reflow ovens, where the paste transforms into solid metallic connections. It's an automated process where every second and every milligram of metal matters. If the tin contains even minor foreign impurities, it can lead to microcracks or tin whiskers, thin thread-like crystals that grow from the solder and can cause short circuits. That's exactly why quality requirements for tin ore and purification methods keep getting stricter. The impact of tin on urban development and global energy is hard to overstate. Sure, we don't build house frames from this stuff, but it's in every lighting control system, every elevator, every safety sensor. The growth of smart cities relies entirely on billions of sensors and controllers, each one held together by tin solder. This makes it a critical strategic resource, with entire regions shaping their economic policy around the battle for control over its deposits. Countries with major cassiterite reserves become key players in the high-tech supply chain. But tin ore extraction comes with serious challenges. Deep open pits and seabed dredging reshape ecosystems, demanding strict reclamation standards. Responsible companies try to minimize environmental impact by restoring forests and cleaning water used in the refinement process. At the same time, recycling is playing a bigger role. Tin is a metal that can be cycled back infinitely. Recycling old circuit boards keeps the metal's high purity with way less energy than mining it from ore. This creates a closed-loop economy, where yesterday's shattered screen becomes the source material for a new device. Interesting fact, tin's been used for millennia. When it combined with copper to create bronze, it gave an entire era of human history its name. Back then, tin was hunted down as aggressively as we hunt for oil or gas today. But while ancient people made swords and cookware with it, today it's become a tool for transmitting information. That's the evolution of this metal's role. From the brute force of bronze weapons to the refined precision of a silicon chip, where tin provides the pathway for electrons to flow. The stone once prized for its ability to make copper hard is now valued for its malleability and conductivity in the micro-world. Technological progress demands ever-increasing quantities of this metal. The growth of renewable energy, solar panels, and electric vehicles creates additional demand. Each photovoltaic panel requires tin connections to harvest the sun's energy. Electric vehicles contain significantly more electronic components than internal combustion engine cars, making this element essential in the fight for climate neutrality. Thus, ancient cassiterite becomes fuel for the green revolution. It's crucial to understand that tin deposits are distributed extremely unevenly across the planet. This creates certain risks for global production stability. Any disruptions in ore supply from major mining regions instantly impact consumer technology worldwide. This pushes scientists to search for new methods of enriching even low-grade ores, as well as developing technology for extraction from deeper horizons. Every foot of new mine shaft or every mile of surveyed deposit is a guarantee that factories keep producing new devices, and the planet's digital network continues to expand. The transformation of tin from mountain rock to solder on a circuit board is an example of how humanity has learned to harness the special properties of materials to achieve remarkable results. It's about tin's ability to be the connecting link. When we look at a chunk of tin ore, we see not just a mineral, but the potential for millions of conversations, terabytes of transmitted data, and the operation of complex mechanisms that ensure our comfort. Tin remains a humble yet irreplaceable hero of the industrial stage, working where no one sees it, at the very heart of machines. Production chains that begin in quarries and end in the clean rooms of high-tech factories are testament to our global interdependence. Tin isn't just a detail on a circuit board, it's the backbone of economies across continents. The continuous flow of ore, concentrate, and finished metal is the circulatory system of industry. Every ton of cassiterite pulled from the earth passes through the hands of thousands of specialists before becoming part of our global information infrastructure. And as we move toward even greater automation and digitization, the role of this stone will only grow, proving that great achievements often start with very small but critically important details. So, tin ore is the real key to modernity. It teaches us to value resources that seem invisible, but without them, the world we know would cease to exist. This is a story about how nature gives us materials, and human ingenuity finds the perfect use for them, transforming heavy ore into the lightness of wireless communication and the speed of data processing. Every grain of cassiterite carries its contribution to global development, remaining an eternal reminder that high technology has its roots in the work of the earth, a stone-born origin. From dark depths to gleaming device cases, the journey of tin is the journey of progress itself. A pinch of metal, a few hundred grams per ton of steel. Add it, and the steel gets 30% stronger. Same weight, same thickness. But it takes a third more force to break it. That pipeline under the North Sea, the one carrying gas at thousands of pounds per square inch? Without this metal, the walls would need to be twice as thick. The project, twice as expensive. Nearly 90% of this metal comes from one country, Brazil, and most of it from one single mine. One company digs it up. One family controls that company. They've been sitting on this for over 50 years without most people ever hearing about it. The metal is called niobium, the quietest monopoly on the planet. But before niobium ends up in a bridge or a rocket engine, it starts as something that looks like ordinary dirt. What happens next involves crushing, floating, and a chemical reaction hot enough to melt through most metals. Araxá, small city in Minas Gerais, Brazil. Population around 100,000. Dusty roads, cattle ranches, a rodeo once a year. But underneath it sits the largest niobium deposit ever found. The mine belongs to CBMM, Companhia Brasileira de Metalurgia e Mineração. Private. The Moreira Salles family holds 70%, one of the wealthiest families in South America. They don't chase headlines. They just dig up most of the world's niobium and ship it out. Here's the thing. This isn't OPEC. No cartel, no politics, no sanctions. Just one company sitting on a geological freak. The pyrochlore deposit, a mineral packed with niobium, is so rich at Araxá that nobody else can compete on cost. Canada mines about 7,000 tons a year. Everyone else splits the scraps. Nobody comes close. And the ore they're pulling out of that pit doesn't look like much. Brown rock. Heavy. But inside that rock sits the element that holds modern infrastructure together. Mining starts open pit. Trucks the size of houses haul pyrochlore ore from benches cut into the hillside. Each load, about 200 tons. The ore contains 2.5% niobium pentoxide. 25 pounds of useful metal per ton of dirt. First step, crushing. The rock goes through jaw crushers, cone crushers, and ball mills until it's a fine, wet slurry. Grey, heavy. Then flotation. The slurry gets mixed with water and chemical agents. Air pumps push bubbles through the mixture. Niobium-bearing minerals grab onto those bubbles and float. Everything else sinks. Workers skim the froth. What comes out is a dark concentrate. About 60% niobium pentoxide. From 25 pounds per ton to 600. Just by letting the right particles float. That concentrate still isn't metal. Turning it into something useful takes one of the most violent chemical reactions in industrial metallurgy. Aluminothermy. Sounds academic. Looks like a war zone. Workers load the niobium concentrate into a steel vessel, packed tight with aluminum powder. Then they light it. Not with a match. With a magnesium fuse that burns at over 3,000 degrees. The aluminum rips the oxygen off the niobium. The reaction hits 4,350 degrees Fahrenheit. The whole charge turns liquid in seconds. No external furnace needed. The reaction generates its own heat. Self-sustaining. The molten mass separates. Niobium iron alloy sinks to the bottom. Aluminum oxide slag floats on top. Workers crack the vessel open and pull out a rough ingot of ferroniobium. 60 to 70% niobium, rest iron. Gray. Dense. Heavy as lead. That ingot is worth roughly $40,000 per ton, and most of it will end up inside steel. Now, why does steel need niobium at all? Because of a trick that engineers stumbled onto, and it changed an entire industry. Microalloying. Add 0.03% niobium to molten steel. 0.03%. A teaspoon of salt in a bathtub full of water. When steel cools, its crystal grains grow. Bigger grains mean weaker steel. Niobium atoms lock into the grain boundaries and stop them from growing. Smaller grains. Tighter structure. 30% stronger. Same weight. The Trans-Alaska Pipeline runs niobium steel. So do gas lines under the North Sea. So does every major bridge built in the last 40 years. And there's a reason this matters beyond construction. SpaceX uses a niobium alloy called C103 for rocket engine nozzles. The exhaust bell on the Merlin vacuum engine, niobium. It handles temperatures above 2,500 degrees Fahrenheit without deforming. Survives re-entry heat, engine thrust, and vacuum cycling. No other affordable material does all three. Put a number on it. The global market moves over 80,000 tons of niobium a year, worth roughly $3 billion. Almost all of it flowing through one company in Brazil. But ferroniobium is the commodity product. The real money starts when you need pure niobium. And purifying it requires a machine that melts metal with a beam of electrons in a sealed vacuum. Pure niobium. 99.9%. Not an alloy. The element itself. Getting there means electron beam melting. A vacuum chamber. A focused beam of electrons hits the metal hard enough to push temperature past 4,400 degrees Fahrenheit. Niobium melts at 4,474. Most impurities evaporate before the niobium does. The beam sweeps back and forth, melting the bar top to bottom. Impurities leave as gas. Pure niobium collects as liquid, then solidifies. 2 passes. Sometimes 3. Each one cleans it further. The final ingot glows silver gray. Smooth. Dense. And worth 10 to 20 times more per pound than the ferroniobium alloy. That corrosion resistance is why surgeons put niobium implants inside human bodies. Your bone grows around it, and the metal just sits there. Decades. No reaction. Corrosion resistance is useful, but niobium has another property that makes it irreplaceable for the biggest machines in physics. Nothing protects this supply chain. No strategic reserve. No backup that can scale fast. Canada produces about 7,000 tons a year. Everyone else combined barely registers. If CBMM's Erixa operation shut down tomorrow, a flood, a strike, a political crisis, the world would burn through existing stockpiles in months. Steel mills would feel it first. Pipeline projects stall. Bridge construction slows. Then the specialty markets start fighting for scraps. Aerospace, medical, particle physics, all clawing at the same shrinking pile. And the strangest part? Nobody talks about it. Niobium doesn't show up on the news. Not on sanctions lists. Not weaponized. China has been prospecting for alternatives. A few junior miners in Africa claim deposits. None of them can match CBMM on cost or scale. The Moreira Salles family runs it like a utility. Stable pricing. Long-term contracts. Quiet enough that nobody bothers looking for a way out. That's the genius of it. The quietest monopoly works because it never gives anyone a reason to break it. Niobium. Named after Niobe, daughter of Tantalus in Greek mythology. Discovered in 1801, ignored for a century. Then someone figured out what a few hundred grams of it does to a ton of steel. And the metal went from a curiosity to a dependency. One mine in Brazil, nearly 90% of global supply, makes steel a third stronger with a pinch, stops particles at CERN, powers every MRI scan, survives rocket exhaust at 2,500 degrees, 80,000 tons a year. One family, no headlines. Next time you drive over a bridge, remember, somewhere in that steel, there are atoms from a hole in the ground in central Brazil. And there's only one hole that matters. Coming up, a liquid metal so dangerous that one broken thermometer can evacuate a building. And they still make thousands of tons of it every year. This single tank holds an entire Olympic pool's worth of fuel. Hard to believe. Look at this. 10,000 gallons in each one of these tankers. I'm standing here in a massive, towering factory right in the heart of America, where these steel giants are born from scratch. This isn't just a workshop. It's a true industrial cathedral, where instead of organ music, you hear the roar of metal, and instead of incense, you smell ozone and white-hot steel. Today we're diving into the process of building a fuel tanker. Those same shiny cigar-shaped missiles that race down highways, loaded with gasoline or diesel. I've already walked these floors, talked to workers whose faces are hardened by heat and labor, and now I'm going to tell you everything. To do that, you need to follow me. Don't fall behind. Ready? Then let's roll. This is going to be incredibly fascinating. First comes the raw material, the lifeblood of a future giant. It all starts not with ore, but with perfectly flat, thick steel sheets arriving on railroad platforms. Picture a sheet of metal 25 feet long and 10 feet wide. It's like a small billboard, only made of steel. And this steel isn't ordinary. It's a special alloyed blend containing chromium for rust resistance and molybdenum for incredible strength. It's engineered to withstand insane pressure, impacts, and constant corrosive attack from fuel. Each of these sheets weighs 3 tons. Workers in bright hard hats, like ants around a giant treasure, use overhead cranes gliding smoothly beneath the ceiling to lift these sheets and carefully stack them. Everything's computer controlled, with laser scanners checking every millimeter of surface for detected defects, microcracks, or irregularities. Only perfect raw material gets the green light to move forward. Now it's time to cut the metal. Sheets roll from the warehouse onto the cutting table. A portal looms over the sheet, and a cutting head hisses along its track. This is a giant plasma cutter. From the nozzle, under massive pressure, erupts a jet of gas heated to tens of thousands of degrees Fahrenheit. It's like a tamed lightning bolt. That jet slices into the metal like butter. Sparks fly in every direction. Like fireworks, the air hums with power, and the smell of ozone fills the shop. A computer program guides the cutter along a perfectly calculated path, carving 2 or 3 panels for the future tank from a single sheet with accuracy down to a 1/4 inch. Each panel has all the necessary openings for future valves and hatches. After cutting, the panels are still hot and a bit rough around the edges. Next up, bending the panels, giving them shape. That's where the real heavyweights come in. 200-ton hydraulic presses. Picture a giant machine that slowly, but with unstoppable force, bends thick steel plate like it's a sheet of paper. A crane feeds in a flat panel, and the machine, pressing it against a massive curved die, transforms it into a perfect arc. That's how the cylindrical sections of the tank and the rounded ends are born. The cylindrical body gets assembled from several of these sections and ends up 50 feet long and 10 feet in diameter. After each bend, workers check angles and radii using special templates and tape measures. Everything has to be perfectly round. Why? Because in a circular vessel, pressure distributes evenly. Any warping, any flat spot, that's a stress point where, under fuel pressure, the tank could rupture. Fuel doesn't tolerate compromises. Welding. That's where the heart of the process is, where separate pieces become one whole. This is where real craftsmanship lives. Welders in masks with automatic ultraviolet filters aren't just handling simple equipment, they're operating automated submerged arc welding systems. That means the welding robot runs along the entire seam, and the arc itself burns not in open air, but beneath a thick layer of special flux powder. This creates a perfectly clean, deep weld, half an inch thick, that's actually stronger than the metal itself. After welding, our tank is one piece, but it's stressed out. Welding creates internal tensions in the metal that need to be relieved, so it's heading for heat treatment. A giant crane carefully lowers the entire 50-foot tank into a massive furnace. The doors close, and the temperature inside slowly climbs to 1,600 degrees Fahrenheit. It rests in that oven for about an hour. This process makes the metal more elastic and releases all the stress. Then the doors open, and out comes a red-hot monster, steam pouring off it. Workers in silver suits start hosing it down with water for controlled cooling. The air fills with a loud hiss, like 1,000 kebabs hitting the grill at once. I laughed and told the guys, "This is your sauna." Now for painting and coating. The cooled tank gets sent to a paint facility. This thing's the size of an aircraft hangar. Then comes the first layer, an epoxy primer that protects against rust. After that, 2 coats of top coat, white for better visibility on the road, and silver with added aluminum powder to reflect sunlight so the contents inside don't heat up. But what's on the inside? That gets special protective coatings. A thin but incredibly tough layer of polyurethane, just 10 millimeters thick. It's completely inert, doesn't react with fuel, and won't crack from vibrations. Workers use laser thickness gauges to check every square inch. No gaps allowed. Installing the fittings is the final touch that transforms the barrel into a high-tech tool. They mount the valves, fill valve on top, drain valve on the bottom, plus an emergency valve to release excess pressure. Each valve is a work of art made from stainless steel, rated for 200 pounds per square inch. They install electronic sensors for fuel level, temperature, and pressure. All the data feeds to a computer in the driver's cab. They mount an inspection hatch, 2 feet in diameter, with hermetic seals. I climbed inside an empty tanker myself, space like a space capsule, and absolute silence, because the 1/4 inch thick walls perfectly dampen sound. Testing, the most exciting and critical stage. First up, hydraulics. They fill the tank completely with water and pressurize it to 250 pounds per square inch. Inspectors with flashlights walk around it for 2 hours, hunting for even a single drop. If there's nothing, the tank is sealed tight. Next, the vacuum test. They pump out the air and check if the pressure drops. And the final, most precise test, pneumatics with helium. They fill the tank with pressurized helium, and special sniffer sensors check for the tiniest leaks. If not even a microscopic helium atom seeps through, the tank is ready for fuel. I watched them fill one test tank with 10,000 gallons of gasoline. Not a whiff of smell outside. The final stage, inspection and marking. A special plate gets stamped with a serial number, manufacturing date, and the empty tank's weight, 20,000 pounds. They slap on Department of Transportation certificates with all the safety specs. And then, a giant crane carefully lifts the finished gleaming tank and mounts it onto the truck chassis. Now it's ready to roll down the highway. Guys, this factory only produces 2 of these tanks per month. Each one's like a little mobile fuel fortress, incredibly safe and reliable. I'm absolutely blown away. From a simple steel sheet to a finished tank, every single detail is thought through. If you see these tankers on the road, know there's incredible work behind them. Thanks for watching. Hit that like button, subscribe, and I'll see you on the next factory tour. Every nuclear reactor on the planet has an emergency brake. Not a button, not a switch. A metal. Drop it into the core, and the chain reaction stops cold. Pull it out too slowly, and you get Chernobyl. The entire world produces just 70 tons of this metal per year. That's 1 railroad car. 1 single car, standing between controlled fission and catastrophe. 5 factories make it. Maybe 6, if you count 1 in China that nobody talks about openly. Fewer factories than NFL teams. And here's the thing. This same metal is sitting inside your phone right now. Billions of devices, atoms-thin layers. The metal is called hafnium, and nobody told you about it. But before hafnium ends up in a reactor or a chip, it has to be ripped from its chemical twin. That separation is one of the hardest jobs in metallurgy. Hafnium never shows up alone. Nowhere on Earth. Never has. It hides inside zirconium. Every sample of zircon mineral ever pulled from the ground has 1 to 3% hafnium baked into it. Always. No exceptions. Now pay attention to this. Zirconium and hafnium are chemical twins. Same atom size. Same valence. Same behavior in almost every reaction you throw at them. So alike that Mendeleev never spotted hafnium when he built the periodic table. It stayed hidden for over 50 years, until 1922, riding on zirconium's back like a stowaway. Think about that. An element hiding in plain sight for half a century. Separating these two costs a fortune. Not because the chemistry is exotic, because the difference between them is almost nothing. So why bother? One property. One single property where they're total opposites. And that property keeps nuclear reactors from melting down. Zirconium is transparent to neutrons. They fly straight through it like light through glass. That's why nuclear fuel rods are wrapped in zirconium. Hafnium does the exact opposite. It swallows neutrons, 600 times more than zirconium. 600. That makes hafnium the emergency brake of every nuclear reactor. Control rods, the metal plates that slide into the core to kill the chain reaction, made from hafnium. When something goes wrong, hafnium rods drop in. They absorb every neutron in their path. Reaction over. American nuclear submarines run on hafnium control rods. Compact, reliable, no second chances needed. Now here's where the money starts burning. To make nuclear-grade zirconium, every trace of hafnium must come out. To get pure hafnium, it has to be stripped from the zirconium completely. Both processes happen at the same plant. Both are brutal. Both start with sand, a specific mineral pulled from beaches in Australia and Africa. What happens next involves 100 repetitions of the same chemical trick and a column of machines taller than a 3-story building. Raw material, zircon sand. Looks ordinary. Slightly heavier than beach sand, faint metallic shimmer. It gets processed into zirconium chloride, a powder that acts like salt with an attitude. Sucks moisture from the air so aggressively that workers handle it in climate-controlled dry rooms. The hardest part comes next. Liquid-liquid extraction. Dissolve that chloride in water. Add an organic solvent. The two liquids grab zirconium and hafnium at slightly different rates. Hafnium moves a tiny bit more into the organic layer. Zirconium stays in the water. A tiny bit. That's the problem. One pass does almost nothing, so they repeat it. 50 times. Sometimes 100. 50 separate extraction vessels chained together in a column the size of a warehouse wall. Liquid cycling back and forth for months. The electricity bill alone would make your eyes water. A single solvent leak shuts the whole line down for a week. Picture a 100-step coin sort where heads and tails are almost the same weight. That's what this machine does. And it never stops. After 100 cycles, hafnium comes out as a chloride compound. Still not metal. Turning it into metal requires temperatures that would melt most equipment. Hafnium chloride gets packed into a sealed vessel with chunks of magnesium. Temperature climbs to 1650 degrees Fahrenheit. Magnesium rips the chlorine atoms off hafnium and bonds with them. What's left behind is pure hafnium. But it comes out as a rough, grey, porous mass. They call it hafnium sponge. Looks like pumice stone someone left in a furnace. Pick it up and it feels heavier than it should. That ugly grey sponge costs over $1,000 per kilogram, more per ounce than gold at certain market points. And it's still not ready for a reactor. Only a handful of companies buy it directly. Framatome in France, Westinghouse in the US. Shipments move in sealed containers under strict tracking. Lose a batch in transit, and people in government offices start asking questions. Vacuum arc furnace. Temperature above 4,000 degrees Fahrenheit. Hafnium melts at 4,050. At that heat, it reacts violently with oxygen and nitrogen. Even a breath of air inside the furnace makes the metal brittle and useless. So the chamber is sealed, air pumped out, replaced with argon. No oxygen, no nitrogen, no room for error. First melt produces an ingot. Composition isn't uniform enough, so they melt it again. Sometimes a third time. The final ingot weighs 10 to 20 pounds. Gray, shiny, looks a bit like stainless steel. Think about what it took to get here. 1 ton of sand, 100 extraction cycles, a magnesium reduction at 1650 degrees, 3 passes through a vacuum furnace above 4,000 degrees, all for a 20-pound bar of metal. That bar still has to prove it's clean enough. In a nuclear reactor, almost pure and pure are two completely different things. Nuclear-grade hafnium must contain less than 1% zirconium. Zirconium isn't toxic, it just lets neutrons pass through. If a control rod has 2% instead of 1, it absorbs fewer neutrons. Under normal conditions, nobody notices. During an emergency shutdown, when every neutron counts, that extra percent could mean the rod fails to stop the reaction in time. 1%. That's the line between safe and not safe. Every ingot gets mass spectrometry analysis. Every batch comes with a chemical passport. The buyers don't take the factory's word for it. Government nuclear programs, defense contractors. They run their own tests in independent labs. Zero trust. The cost of a bad batch isn't money. It's a reactor that won't shut down when it needs to. 5 factories on Earth can meet that standard. And now a second industry is pulling on that same tiny supply. Since 2007, hafnium has had a second life. Inside microprocessors. When transistors shrank below 12 nanometers, the old insulating layer stopped working. Too thin. Current leaked straight through like water through a cracked pipe. Hafnium oxide solved that. A few atomic layers hold the charge where silicon can't. Every modern processor contains hafnium. Phones, laptops, data centers. Microscopic amounts, but across billions of devices, it adds up. A second major buyer pulling on a supply that fills 1 railroad car per year. 1 factory down for maintenance can move global prices. 2 offline at once, and both nuclear and semiconductor start making uncomfortable phone calls. There are no hafnium mines. Not one. Every gram ever produced is a byproduct of zirconium processing. If demand for zirconium drops, hafnium supply drops with it, even if demand for hafnium is going up. 2 industries fighting over a metal that only exists because someone else needed its twin. 70 tons a year. 5 factories. A supply chain so thin that losing 2 of them would send shockwaves through nuclear energy and tech at the same time. Next time you pick up your phone, remember this. Somewhere between the glass and the battery, there are atoms of a metal that doubles as a nuclear reactor's emergency brake. And there's barely enough of it to go around. Next one. A metal they pull from volcanic rock at 3,000 degrees. One country controls 90% of the supply. Every year, humanity produces over 360 million tons of plastic. Most of it doesn't disappear. It decomposes over hundreds of years. But what if instead of oil, we could make plastic from sugar? In the very heart of Thailand grows a crop that can change this. Sugarcane isn't just a plant, but a solar biofactory that transforms light into the material of the future. From its sweet juice is born polylactide, a bioplastic that decomposes naturally. How do they create eco-friendly packaging from simple cane that could save the planet? Watch till the end, and you'll discover the secret the industry has been keeping quiet about. Sugarcane is a true biofabricator of solar energy. It belongs to the grass family and is grown mainly in warm, humid regions, such as Thailand, Brazil, or India. In Thailand, particularly in Chiang Mai, cane occupies thousands of hectares and is a key crop for the agricultural economy. Cane isn't grown from seed. It's propagated through cuttings, pieces of stems that have nodes with buds. They're planted in prepared soil, usually in furrows, at a depth of 2 to 4 inches. After a few days, the buds sprout and new shoots begin to form. This plant is very light-loving, so plantations are located in open areas. It needs lots of water, but doesn't like stagnation, so irrigation must be moderate and regular. Over 10 to 14 months, the cane grows to 7 to 14 feet tall. Its stems are thick, juicy, filled with sweet juice. It's in this juice that sucrose is contained, the basis for sugar production. During growth, the cane actively absorbs carbon from the atmosphere, converting it into organic substances. This makes it not only a source of energy, but also a natural absorber of greenhouse gases. Sugarcane is harvested when it reaches maximum sucrose concentration, usually 10 to 14 months after planting. In Thailand, the harvest season falls during the dry period, from December through March, when the plant is no longer growing but accumulating sweet juice. In many regions of Thailand, manual harvesting is still used. It's hard work performed by experienced workers with machetes. Before this, the plantation is often burned to remove leaves and ease access to the stems. Although this simplifies the process, burning harms the environment, so more and more farmers are switching to green cane. Harvest without fire. Large farms use mechanized combines that cut, clean, and chop the cane right in the field. This is faster, more efficient, and more ecological, though it requires investment. Important: cane residues, bagasse, aren't thrown away. They're used as biofuel, fertilizer, or even for making paper. This is an example of circular economy where nothing is wasted. After harvest, the cane must reach processing as quickly as possible. Otherwise, the sucrose level in the stems begins to drop, and that means quality loss. So logistics here is critically important. Trucks are the most common option in Thailand. Special open platforms or beds with high sides allow transporting large volumes of cane. Buggies or tractors with trailers are often used for short distances, from field to loading point. In some regions where there's appropriate infrastructure, cane is transported by rail cars. This is efficient for large volumes and long distances, but less flexible than motor transport. Water transport is a rare but possible option in areas with canals or rivers. It's used mainly for export or movement between regions. Cane is often not chopped in the field, but transported in whole stems. They're laid horizontally, densely, to minimize losses. At the factory, chopping, pressing, and juice extraction already occur. Large agricultural enterprises use automated loading systems that speed up the process and reduce losses. In smaller ones, work is still done manually or with simple mechanisms. When trucks with sugarcane arrive at the factory, the technological process begins that transforms the green plant into an innovative material, polylactide. This is a complex but fascinating journey where agricultural biomass becomes part of the ecological future. Before the cane enters processing, it's checked for sucrose content. Samples are taken from each batch to determine how suitable it is for production. Then the stems are cleaned of leaves and foreign impurities, manually or mechanically. Then our cane needs to be chopped. For this, the stems pass through mechanical crushers. These are large rollers or rotary machines with sharp blades that cut the stems into small fragments. The goal is to maximally open the cellular structure to ease juice extraction. The chopped cane is pressed in special rollers. Under high pressure, sweet juice rich in sucrose flows out. This juice is collected in reservoirs. The juice undergoes filtration to remove impurities and then is heated for concentration. Next, a process similar to brewing kvass or yogurt is launched. Special bacteria are added that transform sugar into lactic acid. It's like when microbes turn grape juice into wine. Only here it's not alcohol that comes out, but acid. This process is called fermentation. It occurs in large tanks, bioreactors. There, everything is controlled. Temperature, acidity, how many bacteria are there? So they work properly and don't slack off. Lactic acid is the key ingredient for creating bioplastic. It has properties that allow transforming it into a polymer. The lactic acid is purified and subjected to polymerization, a chemical process in which molecules connect into long chains. The result is polylactide, a thermoplastic polymer that looks like granules or threads. These granules or threads are the basis for producing packaging, tableware, textiles, 3D printing filaments, and other products. Polylactide has high transparency, strength, and heat resistance, making it an ideal substitute for traditional plastic. Polylactide granules are poured into special machines, extruders or thermopresses. There, they're heated to the required temperature until they become a viscous mass. The hot mass is passed through forms or dyes. For packaging in bags, the extrusion method is used, that is, pulling hot polymer into long ribbons or film. Cups, containers, spoons, and so on are made by filling corresponding forms with polymer under pressure. To create more complex shapes, like coffee lids, heated film is pressed to the form with a press. As soon as the product is formed, it's quickly cooled, with water, air, or special cooling plates. This is needed so the material hardens and doesn't deform. Finished products are trimmed, polished if needed, checked for quality, and packed for delivery. Before packing, each product undergoes visual inspection or automatic checking for defects, cracks, deformations, irregularities. In large productions, this is done by robotic systems with cameras and sensors. Defective products are often remelted, since polylactide allows reuse without quality loss. After final cooling, polylactide products, still warm from machine touch, set out on their last journey, to the packing line. Here, everything works smoothly. Mechanical arms carefully stack cups in perfect stacks, 50 in each. Product groups are wrapped in biodegradable film or cardboard boxes. Packaging can also be made of polylactide. That is, the product and its wrapper are made from the same material, which simplifies recycling. Afterward, labels are applied with information: polylactide type, production date, batch, disposal instructions. Finished boxes with products are stacked on pallets, wrapped with stretch film, which is often also bio, and sent to warehouses or to customers. Storage temperature is room temperature, but without excessive humidity, so polylactide doesn't start decomposing prematurely. Green packaging is no longer just fashion, but a demand of the times. Videos about plastic harm get millions of views, and brands are looking for alternatives that don't harm the environment. Polylactide from cane is one of the most promising options. After all, cane grows quickly, and the production process doesn't require crazy resources. What if one of the most common metals on Earth has a hidden property that even some engineers still underestimate? A metal that boils like water and vanishes into thin air during production, only to be reborn as gleaming ingots. We see it every day, but almost no one knows what the underground cities where it's mined look like, or what giant machines make the ore ignite like little controlled earthquakes. In this video, you'll discover things you never suspected, and by the end, the main secret will be revealed that will forever change how you think about zinc. Zinc is the fourth most consumed metal in the world, right after iron, aluminum, and copper. That alone tells you just how critical it is for the global economy and industry. Annual worldwide zinc production runs somewhere between 12 and 13 million metric tons. We're talking massive volumes here, which really drives home how irreplaceable this metal is across hundreds of different applications. The main zinc mining regions are China, Australia, and Peru. These three countries together account for a huge chunk of global zinc ore production, making them the key players in the market. For instance, China isn't just the world's largest producer, it's also the biggest consumer of zinc, which reflects its massive industrial growth. Other major producers include India, the United States, Mexico, and Canada. As for reserves, the U.S. Geological Survey estimates that global zinc reserves sit at around 250 million metric tons. Beyond that, there are what we call resource bases, essentially potential deposits that haven't been fully explored yet, or aren't economically viable to mine right now. These are estimated at over 1,800,000,000 tons. These numbers tell us that zinc, unlike some rare metals, will be around for many decades to come, even with consumption on the rise. The biggest user of zinc is the galvanizing industry, which uses it to protect steel from corrosion. This sector accounts for roughly 60% of all zinc produced. This shows just how critical zinc is for construction, automotive manufacturing, infrastructure production, and countless other industries where steel's strength and durability are essential. Without zinc coating, the lifespan of steel products would drop dramatically, leading to massive economic losses and a huge spike in resource demand. 15 to 20% of zinc is used to produce alloys like brass and die casting alloys. These alloys are used in making parts for cars, household appliances, toys, plumbing fixtures, and electronics. Another 10 to 15% goes into making zinc oxide and other chemical compounds. Zinc oxide has a ton of uses, from sunscreens and cosmetics to paints, ceramics, the rubber industry, and even animal feed supplements. Its antibacterial and protective properties make it a versatile ingredient. The rest of the zinc goes into battery production, as a micronutrient in agriculture to boost crop yields, and in pharmaceuticals and dietary supplements, since zinc is essential for the human immune system. When it comes to pricing, like most commodities, zinc prices fluctuate based on global supply and demand, economic cycles, and the situation in major producing and consuming countries. However, demand for zinc remains stable or growing, driven by urbanization, infrastructure development, and the worldwide need to protect metals from corrosion. This makes zinc an important indicator of global economic health. Most zinc is extracted from underground mines. These are entire underground cities stretching hundreds of feet and sometimes several miles beneath the Earth's surface. We're not talking about simple holes in the ground. These are networks of tunnels, shafts, ventilation systems, and hoisting structures. It all starts with exploration. Geologists work like detectives, searching for what's called ore bodies, sections of rock where the concentration of zinc is high enough to make mining it profitable. Now, zinc typically shows up as a sulfide ore, like sphalerite, and it almost always comes bundled with lead, silver, and sometimes copper. Once they've located a deposit, the real work begins: building the mine itself. This involves sinking vertical shafts that serve as the main access points for getting to the ore, hauling materials up and down, and moving equipment in and out. They also create horizontal tunnels, what miners call drifts, that lead straight to the ore veins. The actual ore extraction is where things get dynamic and risky. Miners bring in specialized gear, powerful drilling rigs that bore holes into the rock face, called blast holes. These holes get packed with explosives. Then comes the carefully controlled blast that breaks apart massive volumes of rock. Think of it like a controlled earthquake on a smaller scale. Dramatic, but completely under control. The dusty air is quickly removed by powerful ventilation systems, which also bring fresh air deep underground. The blasted ore is then loaded into massive underground haul trucks or onto conveyor belts using heavy-duty loaders. It's like a non-stop underground highway, constantly moving tons of ore to the main hoisting shafts. From there, the ore is lifted to the surface using powerful elevators or specialized conveyor systems that climb hundreds of feet vertically. At every stage, from drilling to hoisting, strict safety protocols are followed, because working underground demands maximum caution. Once the ore reaches the surface, it still looks like ordinary rock containing only a small percentage of zinc. To extract the valuable mineral, the ore goes through a processing plant, a whole complex of sophisticated processes. The first step is crushing and grinding. Massive chunks of ore feed into crushers that break them down into smaller pieces with a deafening roar. This crushed ore then goes into ball or rod mills, giant rotating drums filled with steel balls or rods. Inside these mills, the ore gets ground down into an extremely fine powder, almost like flour. This is critical to free the zinc mineral crystals from the surrounding rock. The next key stage is flotation. The ground ore powder gets mixed with water and special chemical reagents in large tanks called flotation cells. These reagents selectively stick to the zinc mineral particles, making them water repellent. Then air is pumped through this mixture, creating millions of tiny bubbles. Particles of zinc mineral latch onto these bubbles and float up to the surface, creating foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. That's your zinc concentrate, which can pack up to 60% zinc. Since zinc often hangs out with lead, the plant might run several flotation cycles to separately pull out zinc concentrate from lead concentrate. The zinc concentrate you get, it's still not pure metal. It's got to go through metallurgical processing to turn into actual metallic zinc. And this is where we enter the world of extreme temperatures. If they're using the pyrometallurgical method, the zinc concentrate first gets roasted. The concentrate is heated in special furnaces at around 1,800 degrees Fahrenheit. This burns off the sulfur that's part of the sulfide ore, converting it into zinc oxide. During this process, the sulfur transforms into sulfur dioxide gas, which gets collected and used to produce sulfuric acid, a crucial industrial product. This not only cuts down on air pollution, but also creates an additional valuable byproduct. Next, the zinc oxide gets mixed with coal and heated to even higher temperatures, over 2,200 degrees Fahrenheit, sometimes reaching as high as 2,700 degrees, depending on the specific furnace technology. At these extreme temperatures, a reduction process takes place. The carbon strips away oxygen from the zinc oxide, releasing pure metallic zinc. And here's where that amazing evaporation effect happens. At these temperatures, the metallic zinc transitions into a gaseous state. Basically, it evaporates. Zinc has a relatively low boiling point compared to other metals. So in these furnaces, where the temperature is way higher, zinc literally turns into vapor that rises up and gets captured in special condensers. There, the vapor cools down and condenses, turning back into liquid metallic zinc. This liquid zinc is then poured into molds to create ingots or pellets. Every year, the world builds hundreds of miles of underground tunnels, but almost nobody thinks about what's holding them up above our heads. Picture this: thousands of concrete segments, each weighing several tons, assembled with precision down to the millimeter, forming tunnels where trains blast through at dozens of miles per hour. Now here's the big question: what happens if even one of them is made wrong? Today, we're diving into the place where the backbone of the subway is born, where one tiny mistake can cost millions or more. But there's a detail they usually don't show. Stick around till the end, and you'll find out what's actually hidden inside these concrete rings. Let's start with what a tunnel lining segment is, and why we need it. When a tunnel boring machine grinds its way through soil, you've got to shore up the tunnel walls right behind it, because soil isn't rock and won't hold itself up. The shield pushes forward, and behind it, installers assemble a ring from several segments, usually 5 to 8 pieces plus one keystone. The assembled ring is what you see when you're riding the subway and looking out the window. Uniform concrete sections with bolted connections along the seams. Looks mundane. Actually, an engineering solution refined over more than 150 years. The plant I visited manufactures tunnel segments for the city subway. Tunnel diameter: 21 feet. Each ring consists of 6 segments and 1 keystone. Width of one ring along the tunnel axis: 5 feet. Concrete wall thickness: 18 inches. One segment weighs close to 4,500 pounds. Monthly, the plant ships out about 600 rings, meaning over 4,000 segments. The math comes out monumental. It all starts with rebar cages. This is the exact moment when steel rods transform into a 3-dimensional structure that'll end up inside concrete and keep it from cracking under load. The rods get cut and bent on automated lines. The machine receives a program, selects the right wire diameter, bends it at the specified angle, and cuts it to size. The thinnest rods here are about 1/4 inch in diameter, the thickest around 1 inch. Then the cages are assembled by hand or welding. It's tedious and monotonous, and workers here are clearly grateful when automation handles the whole process. The finished cage gets placed into a steel mold. The mold is probably the most expensive thing in these entire factories after the presses themselves. It's manufactured for a specific project and specific tunnel diameter. One mold costs anywhere from $200,000 to $400,000, depending on the complexity of the geometry, and it's rated for several thousand cycles. Before each pour, the mold gets cleaned of leftovers from the previous cycle and coated with special release compound. Without it, concrete bonds to the steel permanently, and you can't pull the segment out without damage. The lubing process is its own science. Too much creates pores on the concrete surface, too little ruins the mold and wrecks the piece. Seems minor, but at the plant, they train people separately just for this. Next, concrete. They don't pour regular batch plant mix here. Segments get made from special grade concrete with precisely dialed in water cement ratios, aggregate size, and additives. Compressive strength, not less than 6,000 pounds per square inch. For comparison, concrete in typical residential construction runs around 3,000. This stuff is twice as dense and heavy. Additives in the mix ensure waterproofing, because subway tunnels run below the water table, and the concrete has to hold water back completely, not soak it up like a sponge. The mix is prepared in an automated plant right at the factory and delivered to the form by transport conveyor or buckets. They don't pour the entire form at once. They do it in layers with vibration in between. Vibrators plunge into the concrete, and when switched on, the vibrator squeezes out air bubbles from the mix. If you leave air in, the concrete will have voids, and porous concrete lets water through and is less strong. One segment takes anywhere from 45 minutes to an hour, accounting for all the layers and vibration. Rushing here is harmful. This is one of those cases where slower actually means better. The filled form heads into a heat treatment chamber. Steam curing, that's what it's called. The temperature inside, around 100 degrees Fahrenheit. Humidity high. The goal, speed up cement hydration and let the concrete gain sufficient initial strength in 8 to 10 hours, instead of the standard 28 days. After curing, the concrete has about 70% of its design strength, enough to remove the formwork without risk of damaging the product. Demolding, the moment I hold my breath a little every time. The crane operator lifts the top part of the mold, then the side panels swing away, and the segment stands on its own. A concrete arc that was just a sloppy mix 8 hours ago. Looks solid. No wonder. 14,000 pounds of solid concrete with rebar in the center. Next, the segment gets moved by crane to a curing rack, where it'll sit for another 7 to 14 days, until it reaches full design strength. Quality control runs parallel to all this. And it's serious here, because tunnel segments aren't paving stones. Each piece gets marked and assigned a unique identification number. During the pour, they pull test cubes, small concrete cubes measuring 4 by 4 inches, that later get crushed in a press to measure the actual strength of the batch. At the same time, ultrasonic testing of finished segments. The ultrasonic device presses against the surface and measures the speed of the wave passing through the concrete. Dense, uniform concrete gives one reading, concrete with hidden cracks or voids, another. The difference shows up immediately, and that segment gets rejected. Another type of control is geometric. Each segment gets placed on a measurement stand, and all key dimensions get checked. Arc length, thickness, bolt hole positions, surface flatness. Bolt hole tolerance can't exceed 1/32 of an inch. Segments that fall outside tolerances, and it happens more often than manufacturers are willing to admit publicly, either get sent back for rework or scrapped. On large projects, the rejection rate can run anywhere from 1 to 3% of total output. Doesn't sound like much at first, but when a single segment runs $4,000 to $6,000, it adds up fast. A separate curiosity, the waterproofing profile. Around the perimeter of each segment, there's a special groove. A rubber gasket fits in there. When the segments get compressed by bolts into a ring, the rubber deforms and hermetically seals the joint. This rubber profile looks like an ordinary black strip, gets manufactured from a highly specific compound based on chloroprene rubber, withstands pressure up to 120 pounds per square inch, and lasts as long as the tunnel itself, meaning it's designed for a minimum of 100 years. Rubber that'll outlive you and me both. Bit philosophical. Shipping from the factory isn't exactly simple either. The segments are heavy, fragile around the edges, and demand careful handling. They're loaded onto specialized frames, secured with tie-downs, and a flatbed truck hauls them to the construction site. There are limits on stacking height, no more than 3 tiers, because the bottom segments can't take excessive weight from above. At the construction site, they dig a vertical shaft. The segments get lowered underground and assembled into rings right behind the shield as it pushes forward. The shield advances 5 feet, the width of 1 ring, and the crew installs the next one. This rhythm never stops, day or night. I step out of the plant and stop beside a stack of finished segments. Gray, slightly rough, smelling of cement. Totally unremarkable. In a few weeks, they'll be 50 feet below city streets, just sitting there. As long as the city stands. No days off, no maintenance, no attention whatsoever from the people above them. That's the fate of a concrete arc weighing 4,000 pounds. I'd complain, but the concrete doesn't seem to mind. See you on the next tour. Right now, beneath our feet, millions of dollars in platinum, through which liquid stone flows at 2,000 degrees. This is a factory where sand transforms into fiber thinner than a human hair, and somehow comes out stronger than steel. Most people think the most valuable thing here is the giant furnace, but they're wrong. The most expensive part is the invisible chemistry, without which the entire material literally crumbles to dust in seconds. Every factory guards this recipe like a military secret. Without it, there'd be no modern yachts, no wind turbines, no airplane fuselages. Today, we're going where outsiders aren't allowed. And the strangest part, we're saving for the end. The whole process starts with a pile of sand and rocks. They use pure silica sand, limestone, and kaolin clay. We're talking massive volumes. Every single hour, they dump tens of thousands of pounds of this mixture into the furnace. For anyone searching for fiberglass manufacturing technology, understand this. It's not just melted glass. It's a strict chemical formula where every percentage point of borates or calcium determines whether your future boat falls apart in the middle of the ocean. These ingredients get mixed in giant hoppers and fed into the furnace, where absolute fiery chaos reigns. The temperature inside that furnace hits 2,500 degrees Fahrenheit. It's so hot that if you threw a chunk of scrap steel in there, it would vanish faster than you could blink. The glass becomes liquid like water and starts glowing with a blinding orange light. Right now, we're standing next to the main source of danger. This furnace runs non-stop for years. The furnace walls are made of special refractory brick that slowly dissolves into the molten glass. Imagine living in a house that you're slowly eating yourself. After 3 or 4 years, they have to rebuild the entire furnace, and that costs a fortune. But the real magic of this plant is hidden below. Underneath the furnace, they've installed plates called bushings. These are the most expensive pieces of hardware you'll ever see in any industry. Each plate is made from an alloy of platinum and rhodium. Why not steel? Because any other metal would simply dissolve in the hot glass or oxidize within hours. A single one of these parts can cost more than $200,000. The plant has hundreds of them. That means right beneath us, there are millions of dollars worth of precious metals with molten rock flowing through them. Each platinum plate has thousands of microscopic holes. When the liquid glass passes through them under pressure, it comes out in thin streams. And this is where the coolest stage begins, the pull. These streams don't just fall down. They're caught by a winding machine spinning at over 60 miles per hour. The glass is pulled so fast, it becomes 10 times thinner than a human hair before it even has time to cool. If you search online for how fiberglass is made, you've seen these shiny threads, but feeling their speed in real life, that's a whole different story. Here's a huge problem right at this stage. Thin glass is an incredibly brittle material. If these strands just touched each other, they'd instantly grind apart and turn into dust. So while the strand flies from the bushing to the spool, it needs to be lubricated. Every fiber gets coated with a special chemical solution. This is each factory's secret weapon. This solution protects the glass from self-destruction and lets it bond with epoxy resin later. Without this chemistry, fiberglass would just be a pile of useless glass garbage. Now we're watching thousands of strands gather into one thick yarn called roving. A single spool like this can weigh 40 pounds and hold tens of miles of continuous strand. Look at these rows of machines. They run around the clock, creating material for wind turbine blades, yacht hulls, and aircraft parts. The scale of production here is mind-blowing. In a single day, this factory churns out enough fiber to wrap around Earth's equator several times. A lot of people ask why fiberglass is so strong. The secret? Glass in fiber form has no microcracks like regular window glass does. It's pure molecular strength. Take a bundle of this fiber 1 inch thick, and you could lift a truck with it. But working with this stuff is a serious challenge. Glass dust is constantly floating in the air. Walk in here without protective gear, and within 5 minutes, your body starts itching like you fell into a patch of stinging nettles the size of a house. The workers here are used to it, but for a newcomer, it's a real test of endurance. Once the spools are wound, they're shipped to massive drying ovens. That's where the threads fully harden and the chemical protection bonds to the surface. Temperature inside those dryers? 280 degrees Fahrenheit. It's a long haul, 12 to 24 hours. If moisture gets trapped inside a spool, all bets are off. Mold, total loss of strength, you name it. For anyone interested in fiberglass construction, here's what matters. This material doesn't rot, doesn't rust. That's why shipbuilders love it. When you see enormous sheets of fiberglass cloth laid into molds for future vessels, you get why this factory matters. Without these thin threads, we'd still be building heavy, clunky structures out of metal that's terrified of every drop of salt water. The production cycle at this facility is a continuous flow of energy and materials. Every minute the furnace runs costs hundreds of dollars in gas alone. Now add the cost of maintaining platinum bushings and the salaries of specialists who know how to tame molten rock. This is an extremely high-stakes business. Any mistake in the glass formula will cause the strand to start breaking. If a break happens at 60 miles per hour, it creates a massive tangle of filaments that has to be cleaned up by hand, shutting down the entire line. Right now, we're passing the shop where fiberglass is chopped into small pieces 1 or 2 inches long. This chopped fiber is added to plastic to make it stronger. It's used to make parts for your cars, appliance housings, and even smartphones. When you're holding a tough plastic object, chances are there are thousands of tiny glass skeletons hiding inside it, made right here. At the end of our tour, we see the finished goods warehouse. Thousands of pallets stacked with gleaming white spools. They look absolutely peaceful, but inside each one lies the energy of a blazing furnace and the precision of precious metals. This production isn't just industry, it's the triumph of human ingenuity over raw matter. Turning sand into fabric that can withstand ocean pressure or open sea wind. That's what makes me marvel at these plants every single time. If you Google fiberglass applications in industry or fiberglass properties, you'll find thousands of pages of text, but nothing replaces that smell of hot glass and the feeling of static electricity coursing through your entire body on this factory floor. This is where the future of our infrastructure is born. I'm thrilled we got to peek inside this closed-off world. Fiberglass manufacturing remains one of the most secretive industries because every plant guards its own glass recipes and chemical coating formulas. It's a world of big money, extreme temperatures, and massive risks. But it's thanks to this insane process that we have lightweight cars, fast planes, and reliable buildings. I hope you enjoyed this walk through fire and platinum. We saw stone become spider silk and learned why it's so brutally difficult. Make sure to check out my other industrial deep dives where we break down the most fascinating factories on the planet. It was lively, it was scorching, and it was incredibly eye-opening. Thanks for taking this journey with me. See you on the next tour, where we'll find something else massive, complex, and absolutely one of a kind. Stay safe and keep away from molten glass unless you've got yourself a shiny silver heat suit. Worth mentioning here, a lot of people are curious about fiberglass for insulation or making composite materials, and this plant is the very first link in that entire chain. Every composite starts right here, at the platinum bushing beneath that blazing furnace. Without this foundation, there'd be no space rockets, no modern construction. See you in future videos, where we'll unlock the secrets of other off-limits facilities. Let me show you something incredible. This is a substance that weighs more than lead, gold, or any other metal on the periodic table. We're in Oregon, at a unique facility where they purify and process osmium. It's the 76th element that most people have never heard of in their lives, and that's a real shame. Osmium is like the introvert of the chemistry world. It's so rare and specific that most people simply don't encounter it in everyday life. This is extreme physics at its finest. Ready to see this cosmic stuff with your own eyes? Then let's go inside. First thing they told me walking in, don't touch anything with bare hands. Not because it's expensive, though it's expensive too, but because osmium in certain forms releases a compound that irritates mucous membranes and in sufficient concentration can damage your retina. It's called osmium tetroxide. So everyone here wears gloves, and the ventilation here is more serious than in a hospital wing. Great way to start a tour, right? But I'm already inside, cameras rolling, and there's no backing out now. Wish me luck. Now for the numbers, because without them, I don't understand why anyone would even mess with this stuff. Osmium melts at 5,486 degrees Fahrenheit. It's the highest density of all known elements. A matchbox with a volume of about 3 cubic inches, if you made it entirely from osmium, would weigh around 12 pounds. 12 pounds. That's like a small bag of groceries, only the size of your palm. I held a sample like that once. The feeling's bizarre. Your brain's telling you something this size can't weigh this much, but your hand's absolutely not buying it. It's one of those moments where the number in the textbook and the actual sensation in your palm are two completely different things. Another number worth keeping in mind, osmium's melting point, 5,521 degrees Fahrenheit. It's the third hardest metal after rhenium and tungsten among refractory elements, way higher than steel, which melts somewhere around 2,000 degrees. In practical terms, you can't melt osmium in an ordinary industrial furnace. Period. That's why they don't make ingots here, and they don't cast parts like at a regular metallurgical plant. The whole process takes a different route. More on that in a bit. Where does osmium come from? You don't find it like iron. No quarries or mines. Osmium's a byproduct of processing nickel and copper ore. Deep in the mines of South Africa or Canada, they're extracting nickel ore, and osmium just happens to be present in trace amounts alongside platinum, palladium, and iridium. Concentration, 1 to 10 parts per billion. To get a single pound of osmium, you need to process 500 to 1,000 tons of raw ore. That's why the market price sits between $1,500 and $2,000 per troy ounce. For comparison, gold currently runs just over $2,000 per troy ounce. Osmium is nearly neck and neck with it price-wise. The raw material arrives at this facility as osmium-bearing concentrate, a grayish-black powder packed in sealed stainless steel containers. The containers are small, about the size of a coffee can. Inside might be 2 to 5 troy ounces of material. Each one of these cans represents $3,000 to $10,000 of raw material. They arrive in a regular courier van, but with paperwork running several pages and cargo insurance. The exact amount isn't disclosed publicly, but from the manager's expression, it's clear the figure is substantial. And a small sample taken for incoming analysis. Literally a few milligrams of powder that go into a spectrometer. If the composition doesn't match the documentation, the batch gets returned. No discussion. First purification stage, dissolution. The concentrate goes into a reactor with an acid mixture at around 350 degrees Fahrenheit. Osmium converts to gaseous tetroxide during this process, the very compound they warned me about at the entrance. This gas is immediately captured and absorbed by a specialized solution in a sealed tube system. Zero external leakage. The system gets checked for integrity every morning before startup. Next, Chemical reactions convert the osmium back into solid form and store it as what's called osmium sponge, a porous dark powder containing approximately 95% metal. This whole process takes 6 to 10 hours per batch, and there's no rushing it. The reaction proceeds at its own pace, and nobody tries to speed it up. The second stage is hydrogen reduction. The osmium sponge gets placed in a tube furnace, through which hydrogen is passed at a temperature of 1100 degrees Fahrenheit. The hydrogen picks up residual oxygen impurities, and what comes out is metal powder with a purity of 99.9%. This takes another 4 to 6 hours. The tube furnace looks completely ordinary, a metal tube about 3 feet long, hooked up to a gas line. If you didn't know what was happening inside, you'd think someone was just drying laundry. But inside this tube, the powder transforms from a dirty concentrate into one of the purest metals produced commercially in the United States. Stage 3 is pressing and sintering. The powder gets loaded into a steel die and pressed at roughly 3,000 pounds per square inch. You get a small cylinder, about 1 inch in diameter and ½ an inch tall. Looks like a coin, only thicker and darker. Then this cylinder goes into a separate furnace, this time at 2000 degrees Fahrenheit, where the powder particles fuse together into a solid metal. After sintering, the density of the sample is already 22.5 grams per cubic centimeter, very close to the theoretical maximum for this metal. Shrinkage during sintering runs about 15% of the original volume, and you've got to factor that into your calculations ahead of time, because the die has to be created with extra room for exactly that shrinkage. After sintering, each sample is weighed and measured. Weighing here isn't just a formality. The scales are accurate to 1,000th of a gram, because at these metal prices, losing even a few hundredths of a troy ounce is real money. All trimmings, all leftover powder, all fine dust from under the press, collected and returned to the recycling loop. Nothing gets thrown away. Even the wipes used to clean work surfaces go to regeneration. They might contain a few micrograms of metal too. Where does finished osmium go? One application: nibs for premium fountain pens. Osmium is incredibly hard and wear-resistant, so a pen like this can write for decades without noticeable tip wear. That's why you'll see Oz marked on expensive pens next to the manufacturer's name. Another application: electrical contacts in relays and measuring instruments, where you need longevity through millions of cycles, and where ordinary copper or silver wears out faster. And the third area, one they talk about more carefully here, medical implants. Osmium combined with iridium creates an alloy of exceptional hardness, used to make pacemaker components and certain orthopedic devices. The human body barely reacts to this alloy. It's biologically neutral, which in medicine is extremely expensive in the most literal sense. The details of contracts with medical manufacturers, those aren't disclosed here. I asked how much finished metal they produce per month. The answer: 20 to 50 troy ounces. That's 4 to 10 pounds of metal over 30 days of operation. Sounds ridiculously small. But in terms of value, $30,000 to $100,000 monthly from a single facility of this size. And there's a backlog of orders 3 to 4 months out. Demand is steady, supply is limited by nature itself. There won't be more ore, and the number of facilities worldwide that actually know how to handle this metal properly, you can count them on one hand. What do you think will happen when osmium runs out? Drop a comment, because I can't stop thinking about it. But your hand feels something fundamentally different from anything I've held before. Your brain refuses to believe it, but physics doesn't ask permission. That's the whole difference between knowing the number and feeling it in your palm. 12 pounds in your fist, and 0 special effects. So, I know North Carolina doesn't sound particularly exotic, but what's being made here flies at 66,000 feet above the Pacific Ocean and keeps 400 passengers in the air at the same time. This is the factory that produces blades for the GE9X turbine engine series, the largest commercial jet engines in the world today. One of these engines weighs about 9 tons, generates thrust up to 105,000 pounds. Sorry, that's roughly 460 kilonewtons, and costs around $50 million. But we're not here because of the engine. We're here because of one specific part that's about the size of your palm and costs more than a nice car. A turbine blade. In the hot section of the engine, in what's called the high-pressure turbine, there are between 160 and 180 of them per wheel, depending on the stage. Each one weighs roughly 10.5 to 14 ounces. But the conditions it operates in, this isn't engineering anymore. It's straight-up torture for common sense. The temperature of the gases flowing around the blade during engine operation, 2700 to 2900 degrees Fahrenheit. That's higher than the melting point of steel, higher than the melting point of the very material the blade is made from. How it doesn't just melt, I'll tell you in a minute, because it's one of the coolest things I saw at this facility. The blade material is a nickel-based superalloy. The exact recipe is classified, and they didn't tell me the full breakdown, which is fair. But the general principle is known. Each element is responsible for something specific. Take rhenium, for instance. It provides heat resistance and slows down creep. That's when metal under prolonged stress and temperature deforms completely. The raw material cost for a single blade runs from 200 to 300 euros just for the metal, before anyone's even touched it. Now, how it all begins. The blade manufacturing process is investment casting, also known in the industry as lost wax casting. First step, the wax model. An exact replica of the future blade, including all internal channels, is created from wax under pressure in a metal mold. The precision of this mold, plus or minus 20 micrometers. That's about a quarter of the thickness of a human hair. If the mold deviates any more than that, it goes back for refinement. But the wax model is just the outer form. Inside the blade, there are also cooling channels, thin, winding tunnels through which cold air from the compressor gets pumped during engine operation. That's why the blade doesn't melt, even though the surrounding gas is hotter than its own melting point. Inside, air at temperatures of 500 to 600 degrees Celsius flows through and keeps the metal in the working zone. These channels are formed separately, using ceramic cores that get inserted into the wax model before casting. The core looks like a thin, sturdy comb, and it occupies exactly the space where the channel will eventually be. The wall thickness between the blade's outer contour and the internal channel ranges from 1 to 2 millimeters. Any thinner, and the blade becomes brittle. Any thicker, and the cooling can't keep up. Next, the wax model gets dipped into a liquid ceramic slurry and coated with fine ceramic sand. Dip, pull out, dry, and repeat the cycle 8 to 12 times. Each layer dries for 4 to 8 hours. After the final layer, you get a ceramic blob about 10 millimeters thick, hard, rough to the touch, kind of like papier-mâché if papier-mâché were made from space shuttle material. Then this whole thing, with the wax still inside, goes into an autoclave, where at temperatures around 300 degrees Fahrenheit and elevated pressure, the wax melts out through a small opening. Hence the name, lost wax casting. What's left inside is a perfect negative of the blade shape. The ceramic holds its form, the cores stay in place. Now comes the metal pour. This is the part I came for. The molten metal gets heated to around 2500 to 2700 degrees Fahrenheit and poured into the ceramic mold. But they don't just pour it and wait for it to solidify. The mold gets slowly withdrawn from the heating chamber at a rate of about 1/10 to 1/5 of an inch per minute. That withdrawal speed controls how the metal crystallizes. If everything's done right, the entire blade, from root to tip, becomes a single crystal. Not a single grain boundary throughout the entire volume of metal. That's single crystal casting. Grain boundaries, the weakest spot in any metal. That's where cracks start under prolonged stress and heat. If there's only one grain, there's no boundary, no failure points. Heat resistance jumps roughly 30% compared to ordinary polycrystalline casting. After cooling, they break the ceramic shell, just mechanically, with hammers and vibration. Out comes a gray blade with ceramic cores inside. The cores come out in an alkaline solution at roughly 210 degrees. The chemistry dissolves ceramic, but leaves the metal untouched. This takes 4 to 8 hours. After washing, those same cooling channels remain in the center, clean, precise, completely open. Then they check the blade. X-rays reveal pores and cracks inside the metal. Fluorescent liquid catches surface defects. A special probe passes through each cooling channel, verifying it's not blocked by ceramic residue. If even one cooling channel is partially blocked, the blade goes straight to scrap. Not to rework, straight to scrap. Because you can't fix that. The rejection rate at this stage runs 2 to 5% per batch. Doesn't sound like much, but given what each part costs, we're talking real money. After inspection, heat treatment. The blade goes through multiple temperature cycles. First, around 1900 degrees for several hours, then a gradual cool down. This process evens out the internal stresses that formed during casting and locks in the alloy's microstructure. The exact heat treatment protocol? Also classified. When I asked, the manager who was walking me through just smiled and changed the subject. Final stage, protective coatings. First comes a metallic bond coat, nickel and aluminum based, applied using a plasma spray process. That's the foundation. On top of that goes the thermal barrier coating, zirconia stabilized with yttrium. It's ceramic. And it's that ceramic layer that absorbs the first several hundred degrees from the screaming hot gas stream. This layer is between 100 and 2 micrometers thick. The application looks like spray painting in a chamber. The blade rotates, the plasma gun moves along it, following a preset path. But the temperature of the plasma stream during application is around 18,000 degrees Fahrenheit. For comparison, the surface of the sun is about 10,000 degrees. So the tool is nearly twice as hot as a star, but the blade itself doesn't heat up more than 4 degrees, because the entire process is incredibly fast and incredibly precisely controlled. The finished blade goes for final weighing, measurement, and registration. Each one gets an individual serial number and a passport where all parameters are recorded, from the chemical composition of the melt to the results of every control measurement. This document is kept for as long as the engine lives, and that's 20 to 30 years and tens of thousands of flight hours. On my way out, I asked how many blades they made per month. They told me it was in the range of several thousand units across all sizes. They wouldn't give me an exact number. But when you consider that one engine needs several hundred hot section blades alone, and orders for the 9X remain backed up for years ahead, you can imagine the scale. You're the best. Subscribe so you don't miss the next facility. It's going to be even more interesting. Write in the comments where you're from, and maybe next time I'll visit your city. Every year, humanity produces over 4 billion tons of concrete, more than any other material on the planet. It's what our cities, bridges, and roads are built from. But every crack is like a tiny timer ticking toward destruction, started the moment water seeps inside. Now imagine concrete that actually lives, breathes, and heals itself. No people, no repairs. Deep in labs across the Netherlands, USA, and Japan, a game-changing material is being born. Inside it, bacteria or microcapsules that can seal cracks on their own, just like skin healing after a wound. How is this even possible? How did a lifeless material gain the ability to regenerate? Stick around until the end, and you'll find out how scientists brought concrete to life. Self-healing concrete. Sounds like something out of a sci-fi movie, but it's already here. Scientists invented it to solve one of construction's biggest headaches: cracks. Regular concrete starts drying out and cracking over time from temperature swings, moisture, or just plain stress. And a crack isn't just a scratch. Water gets inside, the rebar starts rusting, the structure weakens, and eventually, you're looking at expensive repairs or even a collapse. That's why researchers decided to create concrete that can patch itself up, No human help required. Sounds crazy, but it's actually pretty logical. There are two main technologies that make this possible: microbiological and mineral. The first one uses real living organisms. So-called bioconcrete was developed by Dutch researchers, and the principle is pretty straightforward. They add special bacteria to regular concrete mix, usually Bacillus pseudofermis or Bacillus conii. These bacteria can stay dormant for years, like seeds in dry soil. Along with the bacteria, they add nutrients, usually calcium lactate. And while the concrete stays intact, the bacteria just sleep. But when a crack forms and moisture gets in, they wake up. That's when the real microscopic work begins. The bacteria start consuming the nutrient substrate and, through their life processes, produce calcium carbonate, basically the same mineral that makes up seashells and limestone. That's what seals the crack from the inside, like the concrete is fixing itself. The results are impressive. Micro cracks up to 0.03 of an inch can disappear completely within a few weeks. And all without human intervention, purely thanks to nature that's been built into an artificial material. The second technology is less alive, but no less impressive. Instead of bacteria, it uses chemistry. Tiny capsules are added to the concrete containing an active substance inside. For example, epoxy resin or sodium silicate. These grain-sized capsules are evenly distributed throughout the mix. When the concrete cracks, some of the capsules burst too. The substance inside comes out, fills the crack, and hardens on contact with air or moisture. The result is the material literally heals itself. It's similar to how certain car paints can heal scratches with heat, except this process is way more complex and large-scale. The advantage of this approach is that it works even in dry conditions, where bacteria might not activate. The downside is cost. Creating the capsules is more complex, so this concrete is pricier. But when you calculate the cost of repairing bridges or tunnels, it becomes clear. The payoff is huge. Interestingly, these technologies don't cancel each other out. Some companies are experimenting with combining biological and chemical methods to create concrete that could self-heal under any conditions: underwater, in the desert, or in freezing cold. Testing shows that structures made with this concrete last 2 to 3 times longer than regular ones. Bridges, roads, dams, parking garages, all of this can be made nearly eternal. For example, the Netherlands already built a lakeside lifeguard station using bioconcrete, and after several years, it hasn't needed any repairs. The idea is spreading fast around the world. In the US, these materials are being tested in bridges, in the UK, in sidewalk paving, and in Japan, even in concrete for coastal reinforcements that have to withstand salt water. Regular concrete, even the highest quality, has a shelf life, roughly 50 years. After that, cracks start appearing, water penetrates inside, rebar rusts, and the structure gradually weakens. Self-healing concrete changes these rules. Thanks to bacteria or microcapsules, it can heal microdamage before it becomes a problem. That's why the service life of structures can nearly double, from 100 to 120 years. That means one bridge or building can stand for 2 human generations without major repairs. Sure, this material isn't cheap yet. It costs several times more than regular concrete, on average 3 to 5 times more. But if you look at the long game, it's totally worth it. Maintaining, repairing, and restoring structures costs governments and companies millions of dollars every year. Self-healing concrete cuts those costs to a minimum. Basically, it's like buying a car that changes its own oil and fixes its own brakes. Expensive up front, but then smooth sailing and economical. The Netherlands became the real home of self-healing concrete. Right here, at Delft University of Technology, the idea emerged to add living bacteria to the mix that could repair concrete from the inside. The man behind this idea is Dutch microbiologist and engineer Hendrik Jonkers. Nature inspired him. He noticed that certain bacteria can survive in limestone rock and create mineral deposits, filling micro cracks in stone. That's when Yonkers asked himself, if nature can heal stone, why not make concrete that does the same? In the early 2000s, he started experiments with different bacterial strains, looking for ones that could withstand concrete's alkaline environment and stay viable for years. After numerous trials, the best candidates turned out to be Bacillus pseudofirmis and Bacillus conii, spores that can sleep for decades and activate only when moisture appears. Yonkers added them to concrete along with a food source, calcium lactate. The results were mind-blowing. When the concrete cracked, the bacteria woke up and produced calcium carbonate, which sealed the cracks like natural glue. Yonkers called his invention bioconcrete, and soon the whole world was talking about it. Later, Delft University launched a project to test bioconcrete under real-world conditions. In 2015, the Netherlands built the first lakeside structure using this material. Years later, it remained in excellent condition without any repairs. Now Yonkers' lab is working with construction companies and governments from other countries, perfecting the formula to make it cheaper and more accessible. The USA and UK bet on the mineral technology for self-healing concrete, which doesn't require living organisms, but works through special microcapsules with healing substances inside. These countries are actively investing in research on materials that can automatically restore minor damage without human involvement. The principle is pretty simple, but looks impressive. Capsules or microcapsules filled with special gel, epoxy resin, or sodium silicate are added to the concrete mix. When the concrete surface stays intact, the capsules preserve their contents without reacting with the environment. But as soon as a crack appears, the capsule ruptures and the liquid flows into the damaged zone. On contact with moisture or oxygen, the substance hardens, gluing the crack edges together and returning the structure's original strength. These systems are currently being tested in US Army labs and British research centers, including Cambridge University. In the UK, they're even building experimental road and bridge sections with this material to track how it behaves under rain, vibrations, and temperature swings. American experts went even further. They're experimenting with capsules that can activate multiple times. Inside these capsules are microgels that not only fill cracks, but also expand on contact with water, creating a hermetic barrier against corrosion. This is especially crucial for bridges and skyscrapers in coastal cities, where concrete constantly faces moisture and salts. Test results show that cracks up to a few hundredths of an inch wide can seal themselves in less than a week. And if the damage is larger, the process takes longer, but still happens without human involvement. Such technologies can significantly extend the service life of roads, tunnels, and even military structures, which is especially valuable under extreme loads. Today, I dragged you out to a place where dust isn't a sign of bad housekeeping. It's the smell of serious money and the foundation of everything we call civilization. We're at a cement plant. Look at this landscape. It's like we just landed on Mars, except instead of red sand, everything here is coated in a fine layer of gray powder. Just think about it. We produce over 4 billion tons of this stuff every year. If you tried to stack it all up, you'd get a mountain that would dwarf any skyscraper in New York. We start our journey at the very beginning, the quarry. Just look at these machines. These giant dump trucks look like they escaped from a Transformers movie, but instead of saving the world, they just haul limestone all day long. One wheel on this thing stands about 12 feet tall. That's twice the height of your average pedestrian, who's probably sipping a latte somewhere downtown right now, completely unaware that their apartment is held up by the efforts of these steel monsters. Limestone is the foundation of everything. It's ancient shells and skeletons of sea creatures that decided to die right here millions of years ago, so we could build another shopping mall today. When limestone gets blasted in the quarry, chunks of rock can be the size of a compact car. But for the plant, that's way too coarse. That's where the primary crusher comes in. It's this massive steel jaw that chews through rock as easily as you crunch chips in front of the TV. The noise here is so intense that your noise-canceling headphones would just give up and retire. After the crusher, we get chunks no bigger than 3 or 4 inches. Next, all this mass goes onto a conveyor belt that stretches for miles. It looks like an endless snake crawling through fields and roads, straight to the heart of the plant. Now we enter the raw materials prep shop. This is where the cooks of the industrial world mix their secret recipe. Besides limestone, we need clay, sand, and a bit of iron ore. All of this has to be ground into a fine powder called the raw mix. You can't even imagine how precise this ratio has to be. The lab checks the composition every 15 minutes. If they're off by even 1%, your entire skyscraper might just decide it'd rather lie down than stand up. Chemistry rules everything here. It's pure science, where we make molecules dance to our tune. And now brace yourselves, because we're approaching the hottest spot on the map. This is the rotary kiln. If you ever thought summer in Texas was hot, you knew absolutely nothing about life. This kiln is a gigantic steel tube over 600 feet long. It's tilted at a slight angle and constantly rotating. Inside, it's straight up hell. Temperatures in there climb to 2,700 degrees Fahrenheit. That's so hot that iron starts to weep. At this moment, what we call decarbonization happens. The limestone breaks down, releasing carbon dioxide, and transforms into calcium oxide. This is the moment of truth. The raw material begins to melt and clump into little gray balls called clinker. Clinker is basically a semi-finished product, cement in its embryonic state. Just think about the energy needed to keep a fire like that going. They burn everything here, from coal to old car tires. So, here's something wild. Old tires make excellent fuel because they burn completely at these temperatures, leaving behind nothing but energy for our kiln. It's like nature's own brutal recycling program. When this red-hot clinker exits the kiln, it looks like tiny meteorites that just fell from the sky. It needs to be cooled immediately. Massive fans blast it, dropping the temperature from thousands of degrees down to 160 degrees Fahrenheit in just minutes. The whole thing looks incredibly dramatic. Clouds of steam, glowing metal, and that distinctive crackling sound. But this still isn't cement. The final stage is the last grinding. We take our clinker, add a bit of gypsum to it, about 5% of the total weight, and send it into a ball mill. This is another horizontal tube, but inside it's packed with thousands of steel balls. As the tube rotates, these balls drop and pulverize the clinker into such a fine dust that it becomes softer than the flour your grandma uses to bake pies. The gypsum here is needed, so the cement doesn't set instantly when you add water to it. Without gypsum, construction workers simply wouldn't have time to carry a bucket of mix to the wall. This grinding process is incredibly loud and consumes enough electricity to power a small town. But the result is worth it. Now we have a gray powder that can turn into stone on command. We store it in massive silos, these concrete towers that can reach up to 150 feet tall. Each silo holds thousands of tons of finished product. Look at these trucks lined up in queue. They haul this powder all across the country. Rail cars, barges, bags at hardware stores. Cement is everywhere. Every American indirectly consumes close to 1,000 pounds of cement each year. We literally live inside this material. Our roads, bridges, building foundations, even power plant dams. All of it depends on those gray granules we just saw inside that blazing kiln. People often tell me this is a dirty business. And yeah, it's true. There's no cement without dust and fire. But that's where its raw beauty lies. This is an industry that doesn't tolerate weakness. Everything here is massive, everything scorching hot, and everything operates at the physical limits of what materials can handle. It's a real battle between man and matter, where we force solid rock to go liquid, then solid again. But this time in exactly the shape we need. Next time you're walking down a sidewalk or staring up at bridge supports, Remember the long journey that stone took. From an explosion in a quarry to 2,700 degrees inside a kiln to steel balls in a grinding mill. It's a long road, packed with chemical transformations and incredible engineering genius. We've learned to control processes that took nature millions of years to create, and we're doing it at a scale of billions of tons. I hope you enjoyed this journey through the world of dust and fire. Personally, I always love seeing how something that looks so simple on the surface turns out to be incredibly complex inside. It reminds us that behind every ordinary thing, there's an entire army of people, machines, and scientific calculations. All right, I'm off to clean the dust off my camera, and you, don't forget to look at the world around you a little more carefully. See you at the next factory, where we'll definitely find something huge, loud, and absolutely fascinating. It's interesting that even in our age of digital technology and artificial intelligence, we're still dependent on a red-hot tube filled with limestone. You can write code for a new app, but you can't live in it. You'll still need a foundation, walls, and a roof. And that's exactly why cement plants aren't going anywhere. They're a reality you can't ignore. It's physics you can't hack. And that's what I love most about it. Here, everything is real. Touch this furnace, you'll get burned. Stand under that clinker stream, you'll get buried. No filters, no fakeness, just pure industrial power. We've traveled a lot of miles today, seen tons of raw materials and giant machinery, and every single time, I can't stop marveling at the scale. Humanity, this weird creature that decided caves weren't enough and started turning mountains into powder to build its own mountains out of glass and concrete. It's ambitious, it's bold, and it's very human. And you know what else is human? Subscribing to my channel right now. Alright, that's it. Tour's over for today. The air here's getting too thick, and my lungs are already begging for some clean forest air. But I'm sure tomorrow I'll want to come back to where the big machines work, because that's where you feel the real rhythm of our world. See you. In a world where every second counts, water produces over 50% of all clean energy on the planet. But have you ever wondered what price nature pays for this power? To build one hydroelectric plant, you need more concrete than for 10 skyscrapers. And the river has to be stopped. Its flow gets diverted into a tunnel. The riverbed gets dried out, and a foundation is poured that can withstand the pressure of thousands of tons of water. But behind every such structure lies not just engineering, but also mystery. By the end of this video, you'll discover how water becomes electricity that powers entire cities, and what dangerous price humanity pays for controlling a river. A hydroelectric power plant is where water transforms into electricity. The river's flow gets directed through turbines that spin and generate electrical power. It's a clean energy source with zero carbon emissions, and it works 24/7. But to make this possible, you need to build a dam, a massive structure that holds back the river, creates a reservoir, and controls water flow. The first and most crucial stage of hydroelectric plant construction is site selection. Engineers carefully study the terrain, geology, and hydrology of the region, looking for a narrow section of river with solid, stable banks. The ideal option is a natural gorge between mountains, where water already has significant elevation drop. This reduces the amount of earthwork needed and ensures powerful water pressure on the turbines. At the same time, it's important to have populated areas nearby that need a stable electricity source. The closer to the consumer, the lower the transmission losses. Such location also simplifies construction logistics, material delivery, equipment operation, worker housing. Site selection is a balance between natural conditions, technical capabilities, and human needs. This is where the foundation of future energy infrastructure gets laid. Before starting hydroelectric plant construction, you need to tame the river itself. Its flow gets temporarily redirected into a specially created bypass channel, or tunnel that's built alongside the future dam. This is a complex engineering operation that allows drying out the section where the main structure will be built. Working in the dry is critically important. Concrete work, rebar installation, and foundation work are impossible underwater. Such a river bypass can function for several months or even years while construction continues. After completing the main work, water gets returned to its new channel, now through turbines that start producing electricity. Once the river is diverted, builders move on to preparing the base, the foundation of the future dam. First, they carefully level the ground, remove unstable rock formations, compact the soil, and reinforce it with special materials. Then, concreting begins. They pour thousands of cubic meters of reinforced concrete, layer by layer, creating a monolithic structure. This foundation must be incredibly strong. It withstands not only the massive water pressure, but also possible earthquakes, seasonal water level fluctuations, and decades of operation. A mistake at this stage means disaster risk, so quality control here is maximum. They use laser levels, geodetic sensors, and every batch of concrete undergoes laboratory testing. From this very foundation grows the giant wall that changes the landscape and energy map of the region. The type of construction depends on local terrain and river characteristics. If the banks are solid and located close to each other, they choose an arch dam that transfers water pressure to the side rocks. If the river is wide and the terrain is flat, they build a gravity wall that holds back water with its own weight. In any case, it's a gigantic structure. Height can reach 984 feet, and length can span several hundred yards. For its construction, they use tens of thousands of tons of concrete, delivered by conveyors, mixers, and sometimes even cable cars. Work continues for years, often non-stop, day and night. Hundreds of people work on site: concrete workers, welders, surveyors, installers. Every stage requires precise coordination because a mistake can cost millions. The key stage of converting water into electricity happens in the lower part of the dam, where hydro turbines are installed. These are massive metal structures with blades resembling giant fans. When water from the reservoir gets directed downward under high pressure, it passes through the turbines, forcing them to rotate. This motion transfers to generators, devices that convert mechanical energy into electrical energy. A generator consists of a rotor and stator. When the rotor spins, electric current emerges in the magnetic field. All this happens with incredible precision. Even a small balance disruption can stop the system. To ensure stable operation, turbines get regularly serviced, cleaned of sediment, and temperature monitored. The result is powerful electricity that enters the grid and powers cities, factories, schools.